Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, heavy questions become gentle ones, and the universe is explored at a pace slow enough for tired minds to wander peacefully. Tonight, we are settling in beside one of the strangest questions astronomy can offer. What is the densest thing in the universe? It sounds like the sort of question a child might ask while staring at the night sky, or the sort of question an adult asks after reading one article too many about black holes and suddenly realizing they are brushing their teeth while thinking about collapsed stars. Both are excellent reasons to be here. Density is an unusual idea when you pause long enough to notice it. We live among objects that look large but weigh little, and objects that look small but feel astonishingly heavy. A pillow takes up space with cheerful confidence, yet can be lifted with one hand. A pebble no bigger than a biscuit can surprise your wrist. Size and weight, it turns out, are not loyal companions. Now imagine taking that mismatch and pushing it far beyond ordinary life. Imagine a mountain compressed into something the size of a marble. Imagine a city packed into a spoonful. Imagine matter squeezed so tightly that the rules we use every day begin to complain, protest, and finally resign altogether. Somewhere out there are objects so dense that light struggles to leave them. Atoms are dismantled, and gravity behaves with unsettling authority. Yet before we reach those extremes, we might begin closer to home. Where are you listening from tonight? Is it late evening in a quiet apartment, early morning with rain at the window, or some in-between hour where the world feels paused for a moment? And what is resting nearest to you right now? A blanket, a lamp, a sleeping pet, a glass of water, perhaps a phone, bravely pretending not to be the reason you are still awake. If you find this journey soothing, interesting, or simply a pleasant companion to the end of a long day, I'd be grateful if you liked the video, subscribed, or shared this little calm corner with someone else who might enjoy drifting through strange ideas at a reasonable volume. For now, settle in. Let your shoulders loosen. Let the room be what it is. There is no rush. The densest thing in the universe has managed to wait billions of years already. It can wait a few more minutes for us. To understand extraordinary density, we should first make peace with ordinary density, because this concept hides in plain sight. We encounter it constantly, though most of us rarely announce it with dramatic flair. Nobody picks up a loaf of bread and says, "Remarkable density profile." We simply notice whether it feels light, heavy, solid, airy, awkward, or suspiciously expensive. Density, in the simplest terms, is how much matter is packed into a given amount of space. That is all. Nothing mystical, nothing theatrical, just how crowded the material inside something happens to be. Picture two boxes of the same size. One is filled with feathers, the other with iron nails. They occupy the same volume, but one is much heavier because more mass is packed into that space. The nails are denser. The feathers, though charming, are less committed to efficiency. Water gives us a familiar measuring stick. Some things float because they are less dense than water. Some sink because they are more dense. A log may be large enough to impress everyone at the lake, yet it floats because wood usually contains less mass per volume than water. A coin sinks without ceremony because metal tends to be denser. This explains why ships float despite being made of steel. They are not solid blocks of steel. They contain enormous hollow spaces filled with air. Averaged over the whole vessel, including that empty volume, the ship's overall density is low enough to remain afloat. This is fortunate because cruise passengers generally prefer vacations above sea level. Even in cooking, density quietly shapes experience. Bread rises because bubbles form inside it. Whipped cream expands because air becomes trapped within it. A dense cake and a light cake may contain similar ingredients, yet one feels like dessert and the other feels like a decision. Our own bodies are a patchwork of densities. Bones are denser than muscle. Muscle is denser than fat. Lungs change density each time you breathe. If you fill them with air and float in water, your body becomes slightly more buoyant. Exhale deeply, and you sink a bit more readily. Swimming lessons have long benefited from physics wearing a casual outfit. Yet the word solid can mislead us. Many objects that feel firm are mostly empty space at the atomic level. That table, the chair, the wall, the cup beside you, all seem continuous and substantial. But if we could zoom inward far enough, we would discover atoms with tiny nuclei surrounded by vast regions where particles move in probabilistic patterns rather than neat little circles. If the nucleus of an atom were the size of a pea placed in the centre of a stadium, the electrons would exist far out in the surrounding volume. Between them lies a surprising amount of emptiness, though governed by forces that make matter behave as if solid. So when your hand presses the table, you're not really touching it in the simple everyday sense. Electromagnetic forces are doing the polite work of preventing atoms from merging into one awkward object. This means that much of the matter around us contains room to spare. Nature is not packing atoms like luggage before a budget flight. It is using structures governed by quantum rules, balance, and force interactions. And once you realize ordinary matter is comparatively spacious inside, a new possibility appears. What if that internal room could be removed? What if gravity or pressure could force matter into arrangements far tighter than anything found in stones, steel, oceans, or people trying to fit one more item into a kitchen drawer? That is where our quiet story begins to tilt toward the extreme. Here on Earth, pressure can already change density. Compress a gas and it occupies less space. Deep under the ocean, water is squeezed slightly. Deep inside planets, materials are pressed into forms that differ from what we see at the surface. Carbon can become diamond under intense pressure and heat. Atoms rearrange, structures tighten, familiar substances become something new. The centre of Earth is under enormous pressure from the weight of all layers above it. The iron core is denser than iron found casually lying around on a sidewalk, which is another thing sidewalks rarely permit. Inside Jupiter and Saturn, pressure becomes so immense that hydrogen may behave like a metal conducting electricity. Matter starts adopting forms that would seem absurd in your garage. But planets, impressive though they are only the warm-up act. Stars take pressure into another league entirely. A star is a giant sphere of gas held together by gravity. Gravity constantly pulls inward. The heat from nuclear fusion pushes outward. As long as these effects balance, the star remains stable. It shines, ages, and spends millions or billions of years minding its thermonuclear business. Eventually, however, stars run low on fuel. The outward support weakens. Gravity, patient and relentless, notices the opportunity immediately. For stars like our Sun, the final result may become a white dwarf. This is the remnant core left after outer layers drift away. It no longer performs normal fusion, yet it does not collapse entirely. Why not? Because quantum mechanics intervenes with a rule called electron degeneracy pressure. Electrons resist being forced into the same quantum states. Matter gains a strange stiffness unrelated to temperature. A white dwarf can contain mass comparable to the Sun packed into a volume similar to Earth. Pause there for a moment. The Sun is about 1.3 million Earths by volume. Now imagine compressing roughly solar mass down to Earth size. That is not merely dense. That is reality becoming stern. A teaspoon of white dwarf matter would weigh tons, not metaphorical tons, real tons, the sort that would make your kitchen table reconsider its career path. And yet white dwarfs are still not the densest objects nature produces. If the original star is more massive, gravity can crush matter further. Electrons are forced into protons, forming neutrons. The structure of atoms collapses. Separate nuclei and electron clouds disappear. What remains is an object made largely of neutrons packed together in a sphere only about 20 kilometers across. This is a neutron star. It may contain more mass than the Sun, yet it can fit inside a city-sized sphere. Imagine taking the mass of our star and squeezing it until the whole object would sit comfortably inside a metropolitan area. One moment you're discussing astronomy, the next moment you're trying to place solar mass near public transport. A teaspoon of neutron star material would weigh billions of tons. Different estimates vary depending on exact conditions, but all of them share a common theme. You would not be carrying it home. At these densities, matter behaves in ways still being studied. Neutrons crowd together under forces we do not yet fully model in all details. The crust may contain exotic nuclei in bizarre shapes nicknamed nuclear pasta, because physicists, when confronting terrifying conditions, occasionally cope through cuisine. There may be layers resembling sheets, rods, tubes, and tangled forms shaped by competition between nuclear attraction and electric repulsion. Inside deeper regions, perhaps stranger states emerge. Perhaps superfluids flow without friction. Perhaps particles transform under pressure. Perhaps quarks themselves begin to roam more freely. We will come to that later. Neutron stars can also spin rapidly. Some rotate many times each second. Others possess magnetic fields so strong they would erase credit cards from distances where practical concerns become academic. These are pulsars and magnetars, reminders that density rarely arrives alone. It often brings speed, magnetism, radiation, and an attitude problem. Still, many people hearing all this assume the answer must simply be black hole, and they are not being unreasonable. Black holes form when enough mass is compressed into a region where gravity becomes so intense that escape velocity exceeds the speed of light. An event horizon forms. Beyond it, return is no longer possible. If you continue the mathematics of general relativity inward, the equations predict a singularity, a point where density becomes infinite and known. Physics breaks down. Infinite density sounds like the obvious winner in any contest. But there is a complication. When physicists say a theory predicts infinity in such contexts, it often signals that the theory is incomplete under those conditions. It may mean our equations have reached the edge of usefulness. Not that nature literally contains a neat little point labelled infinity, please do not touch. So does a black hole contain an actual singularity? We do not know. We strongly suspect quantum gravity, a theory not yet completed, would modify the picture. The true interior may involve something else entirely. That uncertainty makes the question, what is the densest thing in the universe? More subtle than it first appears. If we mean the densest confirmed form of matter we can reasonably describe, neutron star cores are leading contenders. If we mean the most extreme objects predicted by current relativity, black hole singularities enter the conversation, though with unanswered questions attached. If we mean the densest stable everyday object available for purchase, perhaps tungsten enters proudly from the side door. Questions, like suitcases, often depend on how you pack them. There is another twist worth noticing. Large black holes, averaged over the volume inside their event horizon, can have surprisingly low average density. Some supermassive black holes are so enormous that this average can be less than water. That does not mean they are fluffy or safe to picnic near. It means geometry and gravity are not always intuitive companions. So the densest thing may not be the largest black hole. It may instead lie in the tiny remnants of dead stars, or in regions we cannot yet observe directly, or in forms of matter still theoretical. And perhaps this is the most comforting part of science. Sometimes the answer is not a final noun. Sometimes it is an unfolding investigation. When people ask what the densest thing in the universe might be, they often imagine some mysterious cosmic object hidden in deep space, glowing ominously, crushing everything nearby, and behaving with the sort of confidence only astrophysics can provide. That is understandable. The phrase itself invites drama. The densest thing in the universe sounds less like a scientific topic and more like a title painted on the side of a spaceship. Yet before we travel outward to collapsed stars, black holes, and matter under impossible pressure, it helps to pause on the word doing most of the work here. Dense. It is one of those words we use casually and constantly, often without noticing how flexible it is. We say a fruitcake is dense. We say fog is dense. We say a forest is dense. We may even say a person is dense, though usually not within comfortable conversational range. In each case, we mean something slightly different. Thick, packed, heavy, crowded, difficult to move through, difficult to understand, occasionally difficult to chew. Science, as it often does, takes a familiar word and gives it a stricter job description. In physics, density means how much mass is contained in a given amount of space. That is the clean version. No insult intended, no commentary on pastries, simply mass divided by volume. How much stuff is packed into how much room? That may sound almost too simple for such a grand question, but many deep ideas begin in plain language. Gravity, motion, heat, pressure, light. Everyday words that become doorways once examined carefully. Imagine two boxes the same size sitting on a table. One is filled with dry leaves, the other is filled with iron bolts. Same outer dimensions, same volume. Yet one is easy to lift and the other causes immediate regret. Why? Because the second box contains more mass in the same space. It is denser. Now imagine two suitcases identical in size. One contains sweaters, the other contains books. If you have ever carried the wrong one upstairs, you already understand density better than you may realize. Volume tells you how much space something takes up. Mass tells you how much matter it contains. Density tells you how efficiently matter is packed into that space, and the universe, as it turns out, is very interested in packing efficiency. Still, our everyday intuition about density can be a bit unreliable, because our brains are strongly influenced by size. Large things feel as though they should be heavy. Tiny things feel as though they should be light. Most of the time this works reasonably well. A wardrobe tends to outweigh a grape. Society remains stable on this point. But exceptions teach us more than rules. A small lump of lead can outweigh a much larger piece of wood. A compact metal tool may feel heavier than a bulky cushion. A little stone can sink while a broad plank floats. The eye judges volume quickly. The hand reports mass honestly. That tension between appearance and reality is where density becomes interesting. Water gives us one of the simplest ways to notice it. If an object is less dense than water, it tends to float. If it is more dense, it tends to sink. Ice floats because solid water forms a crystal structure that spreads molecules farther apart than in liquid form, making ice less dense than water. This small quirk is one of the great conveniences of Earth. Lakes freeze from the top down instead of turning into solid blocks that would make aquatic life considerably less cheerful. Wood often floats because its structure contains air spaces and lower overall density. Stone usually sinks. Steel sinks if it is a compact lump, yet a steel ship floats because shape and enclosed air reduce its average density below that of displaced water, which means a cruise ship and an anchor can be made of similar materials while having very different relationships with the ocean. This is the sort of detail physics enjoys. Our own bodies offer another example. Humans are close to the density of water, which is why swimming is possible and bath time remains mostly manageable. Lungs filled with air lower overall density slightly. Exhale deeply and you become less buoyant. This explains why floating calmly on your back feels easier after a breath in than after a determined sigh about your responsibilities. Bones are denser than muscle. Muscle is denser than fat. Teeth are denser than many things one should not bite. Even within you, matter is arranged with different packing strategies. But then we meet a deeper surprise. Most ordinary matter is not nearly as packed as it feels. That chair beneath you may seem solid and dependable. The wall beside you may feel sturdy. The floor may have spent years convincing everyone it is unquestionably substantial. Yet on atomic scales, these objects contain astonishing amounts of empty space. An atom has a tiny nucleus at its center, made of protons and neutrons, surrounded by electrons occupying quantum states. If the nucleus were enlarged to the size of a marble, the atom itself would be much larger around it, with most of the interior volume not occupied by little billiard ball particles stacked tightly together. Matter feels solid not because atoms are solid chunks pressed flush against one another, but because electromagnetic forces prevent them from passing through each other under normal conditions. When you place your hand on a table, the atoms in your hand do not truly merge with the atoms in the table. Forces push back, boundaries hold. So ordinary solids are, in a sense, structured emptiness stabilized by laws of nature. That phrase may sound dramatic, but it is surprisingly practical. It means there is room inside matter for compression under the right conditions. Not infinite room, certainly. Nature has standards, but room enough that under immense pressure atoms can be squeezed closer than they are in daily life. This is where density stops being a household concept and begins climbing toward astronomy. Before we go there, though, it is worth separating mass from weight, because these terms are often mixed together like ingredients that should have been labelled more clearly. Mass is the amount of matter in an object. Weight is the force gravity exerts on that mass. If you carried a hammer to the moon, its mass would stay the same, but its weight would decrease because lunar gravity is weaker than Earth's. If you somehow carried it to a neutron star, several other problems would arrive first, but its weight would become the least of them. Density uses mass, not weight. It is about how much matter is present, regardless of where the object happens to be. This distinction matters because the universe contains many environments with very different gravity. A rock, a spacecraft, and a potato all participate whether they like it or not. Now consider compression. Take a gas in a syringe and push the plunger inward. The gas occupies less space. Same amount of matter, smaller volume, higher density. This is straightforward because gas particles are already far apart. Liquids are harder to compress, solids harder still. Their particles are already more tightly arranged. Yet under enough pressure, even solids can be squeezed somewhat. Deep beneath Earth's crust, minerals exist in forms that only high pressure allows. Carbon becomes diamond when atoms adopt a tightly bonded crystal structure. Metals in planetary cores are denser than near the surface because layers above press downward with enormous force. Then we reach planets like Jupiter, where pressure rises so dramatically that hydrogen may become metallic. The most common element in the universe begins behaving in ways it certainly does not on your stovetop. Pressure changes structure. Structure changes density. And gravity is the greatest pressure machine we know. Large masses pull themselves inward. The more mass gathered, the stronger the inward squeeze. A small asteroid can remain loose rubble. A larger planet becomes rounded by self-gravity. A star becomes a giant sphere because gravity insists on central organization. For stars, density becomes a balancing act. Gravity pulls inward, heat from nuclear fusion pushes outward. As long as the star can fuse elements in its core, that outward pressure resists collapse. The star survives in a long argument with itself. Eventually fuel runs low. Then gravity gains leverage. The outer layers may expand or drift away, while the core contracts. Matter becomes denser and denser. In some stars it stops as a white dwarf. In more massive cases, collapse continues into neutron stars. In still more extreme scenarios, black holes form. Each step involves matter packed into smaller regions, crossing thresholds where new physical rules become important. This is worth lingering on because many people imagine density as merely more weight in less space. That is true, but incomplete. At cosmic extremes, increasing density means changing the very state of matter. A log is wood, whether large or small. A gold bar is gold, whether thick or thin. But compress stellar matter enough, and atoms themselves break down. Electrons may be forced into protons. Nuclei crowd together. Particles behave collectively. Quantum pressures arise. Familiar chemistry resigns politely. Dense matter is not just ordinary matter squeezed like laundry in an overfilled drawer. it can become something fundamentally different. That is why the question, what is the densest thing, is so rich. It is not merely asking for a heavy object, it is asking where nature pushes matter to the edge of known behaviour. Even numbers can mislead us here. Lead is dense by everyday standards. Osmium and iridium are denser still among stable elements. Tungsten feels satisfyingly serious in the hand. But compared with white dwarf matter, these materials are practically spacious suburbs. Compared with neutron star matter, they are open countryside. And compared with whatever lies inside a black hole, our measuring language starts sweating. Still, one should not underestimate ordinary density. It shapes architecture, engineering, biology, geology, and cooking. Bread rises because gases create lower density structure. Oil floats on water because it is less dense. Hot air balloons rise because warmed air becomes less dense than surrounding air. Continents float atop denser mantle rock through long-term geological behaviour. Even weather depends on air density differences that drive movement. Density quietly organises daily life. Warm air rises, cold air sinks, cream separates, ice floats, metals sink. Mountains have roots in the crust. Rain falls through thinner upper air into thicker lower layers. A room heats unevenly. A loaf bakes differently depending on trapped moisture and bubbles. You may not wake each morning announcing, "Today, I shall respect density," but you live inside its consequences constantly. There is also a psychological charm to the concept. Density reveals how deceptive appearances can be. Large does not always mean massive. Small does not always mean slight. Spacious things can be light. Tiny things can be astonishingly substantial. The same lesson appears in astronomy. Some stars are huge but diffuse, with outer layers thinner than good laboratory vacuums. Red supergiants can span vast distances while having low average density. Meanwhile, a neutron star, only city-sized, can outweigh the Sun. The universe enjoys contrast. So when we ask what dense means, we are really asking several connected questions. How much matter fits into a space? How strongly is that matter compressed? What state does the matter take under those conditions? How does gravity help or hinder the packing? And at what point do our current theories stop giving tidy answers? These are calm questions, but not small ones. If you hold a pebble and a sponge of equal size, you feel one answer. If you watch a ship float and a key sink, you see another. If you imagine a star collapsed into a sphere 20 kilometers wide, you begin stepping into stranger territory. That path from pebble to neutron star is smoother than it first seems. It is all density, just played at different volumes. Take a glass of water and place it on a table. It does not look like a gateway to cosmic understanding. It looks like a glass of water. Quiet, practical, transparent, and perhaps mildly judgmental if left untouched too long. Yet inside that simple glass lives one of the clearest demonstrations of density in everyday life. Drop in a grape and it sinks. Add an ice cube and it floats. Stir in some salt and the behaviour may change. Place a wooden spoon in the same glass and part of it stays above the surface as though it has decided halfway is enough effort for one day. These familiar moments seem ordinary because they are ordinary. They happen in kitchens, lakes, bathtubs, ponds, harbours, and occasionally in science classrooms where someone is trying to make buoyancy feel exciting before lunch. But they are also expressions of one of the most important principles in physics. Whether something sinks or floats depends mainly on density. That is the short answer. The longer answer is more interesting because objects do not simply possess a secret label saying sink or float. They negotiate with the fluid around them. To begin gently, imagine placing an object into water. The water already occupies space. To make room for the object, some of that water must move aside. This is called displacement. The object pushes water away and takes its place. Now, here comes the key point. Water pushes back upward on the object. This upward force is buoyancy. It exists because pressure in a fluid increases with depth. The water lower down presses harder than the water higher up, creating a net upward push. If that upward buoyant force is greater than the object's weight, the object rises. If it is less than the object's weight, the object sinks. If the force is balanced, the object floats peacefully, often looking quite pleased with itself. Density determines how likely this balance is to favour floating. An object less dense than water can displace enough water to support its weight before becoming fully submerged. It floats. An object more dense than water must sink deeper, and if it cannot displace enough water even when fully submerged, it continues downward. That is why a pebble sinks while a cork floats. Same planet, same gravity, same water, different density. The pebble contains more mass packed into its volume than the cork does. The cork, with its many tiny air-filled cells and lightweight structure, has lower average density than water. The pebble does not. Already we can see something subtle. Density is not just about material. It can also be about structure. A block of steel sinks. A steel ship floats. This sounds contradictory until we remember that the ship is not a solid steel cube. It contains vast empty spaces filled with air. When considering the whole vessel, steel hull plus interior air plus all that enclosed volume, the average density can be lower than water. That is enough for flotation. This is fortunate because international travel by immediately sinking metal block would have faced marketing challenges. A ship floats by displacing a large amount of water while weighing less than the displaced water would weigh. Its shape matters enormously. A bowl-shaped hull can hold much more enclosed volume than a compact chunk of metal. If you crush a can into a dense lump, it sinks more readily than when it encloses air. Same material, different average density. Submarines make elegant use of this principle. They adjust buoyancy by taking water into ballast tanks or forcing it out with compressed air. Fill tanks with water, average density increases, submarine sinks. Push water out and replace with air, average density decreases, submarine rises. A submarine is essentially a machine that negotiates with density for a living. Fish do something similar biologically. Many species use swim bladders, internal gas-filled organs that help regulate buoyancy. By adjusting gas volume, they can hover at chosen depths without constant swimming. This is efficient, graceful, and far superior to many human attempts at standing still in water. Humans too participate in the floating question. We are close to the density of water overall, which is why swimming is possible, and why panic is generally less helpful than calm breathing. Lungs play a major role. Fill them with air, and your average density decreases slightly. You become more buoyant. Exhale strongly and you become denser relative to the surrounding water. That is why floating on your back often becomes easier after a deep breath in. It is also why beginners are frequently told to relax. Tension leads to frantic motion, poor breathing, and the mistaken belief that water has become personally hostile. Body composition matters as well. Fat tissue is generally less dense than water, while muscle and bone are denser. This means two people of similar size may float differently. The laws of physics remain polite but impartial. Now let's look at ice, one of the most charming exceptions in nature. Most substances become denser when they freeze. Molecules slow down and pack more tightly in solid form. Water does something unusual. As it freezes, hydrogen bonding arranges molecules into an open crystal lattice that takes up more space than the same molecules do in liquid form. The solid becomes less dense than the liquid, so ice floats. This small oddity has enormous consequences. Lakes freeze from the top down. A layer of ice forms at the surface and can insulate the water below, allowing aquatic life to survive winter. If ice sank, bodies of water could freeze progressively from the bottom upward in cold climates. Ecosystems would be transformed. Seasonal survival would be much harder. Many life forms owe something to floating ice, whether they know it or not. Ice cubes in drinks owe it everything. Salt water introduces another twist. Dissolved salt increases the density of water. That means some objects float more easily in seawater than in fresh water. People often notice this in the ocean. Floating can feel easier at sea than in a lake. The Dead Sea is famous for this effect. Its extremely salty water is so dense that human bodies float with unusual ease. People appear to recline effortlessly on the surface, often holding newspapers for photographs, as though buoyancy itself has become theatrical. Egg experiments in kitchens use the same principle. An egg may sink in plain water, but float in salty water once the water becomes dense enough. This has convinced generations of children that science is either magical or very interested in breakfast. Air, though invisible, also has density. It is simply much lower than water's density. Hot air balloons rise because heating air makes it expand. The same amount of gas occupies more volume, reducing density relative to cooler surrounding air. The balloon system then becomes lighter overall than the air it displaces, and upward buoyancy does the rest. So a balloon rises not because heat is inherently upward, but because density differences create a buoyant force. Weather itself depends on this principle constantly. Warm air rises, cooler, denser air sinks. These motions help drive winds, storms, cloud formation, and the general habit of the atmosphere to keep things interesting. If you have ever watched steam rise from tea, felt warm air near a heater gather higher in a room, or noticed basements staying cooler, you have seen density shaping daily life again. Even cooking makes use of it. Oil floats on water because it is less dense and does not mix readily. Cream can rise in milk because fat droplets are less dense than the surrounding liquid. Bread becomes lighter because gases produced by yeast create bubbles throughout the dough, lowering average density. A loaf that rises beautifully is partly a triumph of trapped gas. Pancakes, soufflés, whipped cream, meringue, sponge cake. All are, in some sense, culinary negotiations with density. Some succeed magnificently. Others become cautionary tales. Now it is tempting to think sinking means failure, and floating means success, but physics does not moralize. Gold sinks, logs float, a stone drops, a lily pad rests, anchors sink exactly as intended. Boats float only when designed carefully. Each outcome reflects a relationship between object and fluid, not a cosmic reward system. Shape can complicate intuition further. A flat steel needle may sometimes rest on water briefly due to surface tension, even though steel is denser than water. The surface acts like a stretched film because of molecular cohesion. Small insects exploit this by walking on water. They are not breaking physics, they are using a different part of it. Likewise, clay can sink as a ball but float as a bowl if reshaped to displace more water. Children discovering this in school experiments often feel they have outsmarted nature. In truth, they have joined a long tradition of engineers. This relationship between volume, shape, and density becomes especially important when we scale upward. Massive cargo ships, floating docks, offshore platforms, and naval vessels all depend on careful control of average density in displaced water. Too much load lowers the hull deeper into the water. Take on enough, and the vessel may lose reserve buoyancy. This is why overloading boats is dangerous. The margin between floating comfortably and becoming a cautionary story can be smaller than optimism suggests. Now let us widen the lens slightly. Why does this matter for a video about the densest thing in the universe? Because everyday floating and sinking train intuition for much grander ideas. Density decides whether rocks settle in molten planets. Density helps layer Earth into crust, mantle, outer core, and inner core. Density influences whether gas clouds collapse into stars. Density affects white dwarfs, neutron stars, and the fate of collapsing matter. The same concept that explains an apple sinking in a bowl also helps explain why a dead star can become an object the size of a city with more mass than the Sun. The scales differ wildly. The principle remains recognizable. That continuity is one of science's quiet pleasures, A child dropping pebbles in a pond and an astrophysicist modelling stellar remnants are not doing the same work, but they are touching the same laws. One asks, why did that sink? The other asks, what happens when gravity compresses matter until atoms fail? Both are asking density questions. There's also something comforting about this. The universe is not made of one set of rules for kitchens and another for galaxies. It is stitched together by patterns that repeat across scale. Water supports a wooden spoon, an atmosphere lifts a balloon, a sea carries a ship, a star collapses until new forms of pressure resist gravity. Matter settles, rises, compresses, expands, floats, falls. Different scenes, same logic. If you look around the room you're in now, density is everywhere. The mug on a table presses downward because of its mass. The air above you has weight and pressure. Dust settles slowly through denser lower air. A cushion springs back because material structure traps space. The mattress beneath someone sleeping nearby may contain foam cells, coils, fibres, and air arranged to manage comfort through controlled density. Even silence in a room is carried by air dense enough to transmit sound. None of this feels dramatic because familiarity disguises wonder. Yet once noticed, it becomes difficult to unsee. A spoon sinks because of packed matter. A cork floats because of trapped space. A cloud hangs because tiny droplets interact with moving air. A continent rides atop denser rock over geological ages. A star balances collapse with heat. The universe keeps returning to the same question. How much stuff is packed into how much room? And what happens next because of it? Tonight we stayed with water, ships, eggs, lungs, balloons, and ice cubes. These are friendly examples. They let us practice without requiring a telescope or existential preparation. Ordinary objects feel solid and crowded, yet atoms contain far more emptiness than most people suspect. If density can already shape oceans and weather, what happens when that hidden empty space starts to disappear? Pick up almost any object near you, or if you are already comfortably settled and have no intention of interrupting that excellent decision, simply glance at something nearby. A mug, a book, a table leg, a phone, a wall doing its best to look dependable. Whatever you choose, it appears solid. It seems filled, complete, continuous. Your senses report that the object occupies its space thoroughly, with no nonsense and no gaps worth mentioning. If you tap it, it resists. If you lean on it, it pushes back. If you drop it on your foot, it becomes unforgettable. And yet, one of the strangest truths in physics is that ordinary matter contains enormous amounts of empty space. Not metaphorical emptiness, not emotional emptiness, structural emptiness. The everyday world feels packed and firm, but on atomic scales, matter is surprisingly spacious. This idea can sound absurd at first, because our instincts were not designed for atoms. Human intuition evolved for fruit, stairs, weather, and avoiding unfortunate decisions. It did not evolve for visualizing nuclei, electron clouds, or quantum structure. So let us approach gently. Everything around you is made of atoms. Different combinations and arrangements create wood, glass, metal, skin, stone, tea, stars, and regrettable kitchen experiments. Atoms are the building blocks of ordinary matter, though building block can mislead us if it makes you picture tiny Lego bricks snapped tightly together. Atoms are stranger than bricks. At the centre of each atom is a nucleus containing protons and neutrons. This nucleus holds almost all the atom's mass. Around it exists a region occupied by electrons, not as little planets orbiting neatly in circles, but as quantum probability distributions describing where they're likely to be found. Already we have entered territory where reality politely ignores our preferred diagrams. The crucial point is scale. The nucleus is tiny compared with the overall size of the atom. Very tiny. If an atom were enlarged so that its nucleus were the size of a marble, the atom itself might be roughly the size of a sports stadium. The electrons would occupy the surrounding region, and most of that stadium would be empty space in the everyday sense of not containing dense central matter. So the table beside you, which feels reassuringly solid, is made of atoms whose heavy centers are separated by relatively vast atomic distances. Why then does the table not feel like a ghostly cloud? Because solidity does not require packed fullness, it requires forces. When you place your hand on a table, the atoms in your hand do not crash through the atoms in the table, because electromagnetic interactions between electron clouds create powerful resistance. Quantum rules also prevent identical particles from piling into the same states in simple ways. You feel that resistance as touch. In daily life, solid means stable structure plus force-based exclusion, not little billiard balls pressed seamlessly together. This distinction matters enormously. It means matter can seem full while containing room, and room means compressibility under the right conditions. Now, before imagining someone squeezing a sofa into a raisin, we should be fair. Ordinary solids are not easily compressed. Their atoms already sit in energetically favourable arrangements, and electromagnetic repulsion pushes back strongly if forced closer. That is why walls remain inconveniently present. Still, there is hidden space in the architecture of matter. Under sufficient pressure, atoms can be pushed closer together. The electrons and nuclei rearrange, structures change, density increases. The universe, as usual, is more than willing to provide sufficient pressure. Let us stay small for a moment. Take carbon. In graphite, carbon atoms arrange in sheets that slide past one another. This is why pencil marks appear, and why pencils continue their quiet service despite keyboard competition. In diamond, carbon atoms form a rigid three-dimensional network. Same element, different arrangement, different properties, greater hardness, different density. Nothing magical added. The atoms were simply packed and bonded differently. This is a recurring lesson. Matter is not only about ingredients, it is also about arrangement. The same atoms can produce softness, strength, brittleness, transparency, conductivity, or resilience depending on how they are organized. Snow and ice are both water, yet one is airy and one is firm. Bread dough and baked bread contain similar components, yet trapped gas changes texture and density dramatically. Coal and diamond are both carbon, though one is rarely presented in velvet boxes. Arrangement matters. Now consider metals. In many metals, atoms form repeating crystal lattices. Electrons move in ways that allow conductivity. The atoms are relatively close compared with gases, giving metals their familiar density and solidity. Lead feels heavy because its atoms are massive and packed fairly efficiently. Aluminum feels lighter because its atoms are less massive and the overall density is lower. A large aluminum pot can weigh less than a small lead object. Again, size misleads. Packing and atomic mass tell the real story. Liquids offer another useful perspective. In a liquid, atoms or molecules are close together but not fixed rigidly in place. They can slide past one another. That is why water pours, waves, splashes, and occasionally escapes containers in ways nobody appreciates. Gases are more spacious still. Molecules move freely with much larger average separations. This is why gases are easy to compress. Push a gas into half the volume, and particles simply have less room to roam. Solids resist compression more because their particles are already near one another. Yet near at human scale still contains atomic spacing that can shrink under enough pressure, and pressure, in physics, is simply force applied over area. Add enough of it, and nature begins renegotiating structure. Deep inside Earth, pressures rise enormously. Materials in the mantle and core exist in forms impossible at the surface. Iron behaves differently under core conditions than in a workshop. Minerals transform into denser phases, go deeper into giant planets, and hydrogen itself can become metallic under immense pressure. The simplest element starts conducting electricity like a metal because atoms are squeezed so closely that electrons behave collectively. This should reassure anyone who suspects the universe enjoys surprises. Then we reach stars. A star is mostly hydrogen and helium, but under the star's own gravity, that gas is compressed into dense plasma. In the core, pressure and temperature become high enough for nuclear fusion. Matter there is far denser than the air around you, yet still nowhere near the limits we will soon discuss. When stars exhaust fuel, gravity can compress matter far further, and this is where atomic emptiness becomes central to our story. As a stellar core collapses, atoms are squeezed tighter and tighter, electrons become crowded, quantum mechanics resist further compression through electron degeneracy pressure. If conditions allow, collapse may stop at a white dwarf. A white dwarf packs roughly solar mass into Earth-like size. Think about that using our current topic. The ordinary atoms in that matter are no longer arranged as in wood, rock, or steel. Electron behavior under intense pressure supports the object. Matter has entered a state unlike anything in ordinary life, yet gravity may demand more. In larger, collapsing stars, electrons are pushed into protons, forming neutrons. Atoms as we know them cease to exist. The empty architecture of atomic space is largely bypassed. Matter is crushed into neutron-rich form. This produces a neutron star. So when people say a neutron star is incredibly dense, what they really mean is that the spacious atomic structure familiar to everyday matter has been radically overcome. The cozy distances inside atoms no longer define the object. That is an extraordinary thought. Everything around us depends on atoms being roomy enough, stable enough, and governed by forces that preserve structure. Your chair, your bones, your lamp, your spoon, your blanket, all rely on atoms having a certain scale and behavior. Change that enough, and the world of ordinary objects disappears. Now, perhaps you're wondering how we know atoms contain so much empty space, if nobody has ever leaned inside one with a flashlight. The answer came through experiments. Early in the 20th century, Ernest Rutherford and colleagues fired alpha particles at thin gold foil. They expected, under older atomic models, that particles would pass through with modest deflections. Most did, but a few bounced sharply backward. Rutherford famously compared this to firing a shell at tissue paper and having it come back at you. This suggested that most of the atom was empty, with a tiny, dense, positively charged nucleus causing rare but dramatic deflections. That experiment transformed atomic theory. The atom was not a soft pudding of spread-out charge. It had a compact centre and lots of room around it. Since then, deeper physics has refined the picture tremendously, but the broad lesson remains. Matter is not packed the way it seems from our scale. This can create delightful perspective shifts. A diamond ring feels solid and precious, yet it is built from atoms with spacious geometry. A steel bridge feels massive, yet its atoms are mostly organised emptiness held by electromagnetic forces. Your own body, though wonderfully real and deserving of hydration, is composed of atoms that are mostly open internal structure by scale. We are, in a technical sense, intricate patterns of concentrated nuclei and active electron systems arranged with astonishing precision. That sounds grander than mostly empty space, and also less likely to upset dinner conversation. Still, one should be cautious with the phrase empty space. It does not mean nothingness in the philosophical sense. Quantum fields exist, forces operate, probabilities matter, energy states matter. It is not empty like an abandoned warehouse. It is empty in the sense that dense central mass is not filling every region continuously. That subtlety matters, because otherwise people imagine atoms as miniature solar systems, floating in vacuum exactly like planets around stars. Reality is more quantum, less tidy, and considerably less willing to pose for diagrams. So why did nature choose such spaciousness? In one sense, it did not choose. Atomic structure arises from the laws governing charged particles, quantum states, energy minimization, and fundamental constants. Electrons occupy allowed states around nuclei. Those states have characteristic scales. Chemistry emerges from these patterns. If atoms were much smaller or packed differently under normal conditions, chemistry as we know it might not exist. Solids, liquids, molecules, biology, and late-night tea mugs might all be very different. The roomy scale of atoms helps make the familiar world possible. And yet, because that room exists, density has somewhere to go under pressure. This is why the topic of densest things in the universe begins not with black holes, but with your table. The table demonstrates stable, ordinary matter. The atom explains why ordinary matter is not maximally packed. Pressure reveals that packing can increase. Stars provide the machinery. Collapsed stars reveal the consequences. It is one continuous story. There is also something calming in realizing that firmness is relational. What feels absolute at our scale is contingent at another. A wall feels impenetrable to you, but at atomic scale it is mostly structured spacing. A steel beam feels rigid, but under geological pressure it can deform. A planet feels permanent, but stars can recycle worlds into plasma. Scale changes meaning. Dense for a loaf of bread differs from dense for tungsten. Dense for tungsten differs from dense for white dwarf matter. Dense for white dwarf matter may differ from what occurs in neutron star cores. Language stretches as reality escalates. For now, the essential idea is this. Atoms leave far more room than our senses suggest. Ordinary matter is efficient enough for daily life, but far from the ultimate packing limit. That hidden spaciousness is why matter can be compressed dramatically under extreme conditions, and once compression begins, gravity becomes the great organizer. Set a book on a pillow, and the pillow sinks slightly. Stack 3 books, and it sinks more. Add a sleepy cat, and the system becomes scientifically complicated but visually excellent. We understand this instinctively. More weight pressing downward changes shape. Pressure at its heart is not a mysterious force reserved for laboratories and exploding diagrams. It is simply force spread over an area. Push gently with an open hand and the sensation is mild. Press the same force through the tip of a pencil, and it becomes persuasive very quickly. The world is full of matter responding to pressure. Cushions compress, tires deform, soil compacts, snow packs into ice. Bread dough changes under a rolling pin. Even mountains slowly bend rock deep below their peaks under the weight of their own existence. Tonight, though, we're interested in what happens when pressure goes far beyond furniture, weather, or baking. We're following a path from everyday matter to the most crowded states the universe can produce. And to do that, we begin with something ordinary and strange. Most matter contains room inside it. Atoms, as we explored before, are not solid little marbles jammed edge to edge. They have tiny nuclei surrounded by electron regions, with surprisingly large relative distances between those scales. Matter feels solid because of forces and quantum rules, not because every inch is packed full of central mass. That hidden room means one thing immediately. Matter can be squeezed. Not infinitely, not casually, and not by stepping on your phone. But under sufficient pressure, the spaces between atoms and molecules can shrink. Structures can reorganize. Density can increase. This happens all around us in modest ways. Take air in a bicycle pump. As the handle is pressed, the same amount of gas occupies less volume. Molecules are pushed closer together, pressure rises. The pump grows warm because compression can also raise temperature. Physics likes to multitask. Liquids are harder to compress because their molecules already sit close together. Solids are harder still. Yet harder does not mean impossible. Even steel compresses slightly under load. Concrete shortens under immense force. The Earth itself flexes under tides caused by the moon and sun. Whole planets respond elastically to gravity. Nothing in the physical world is perfectly rigid. That is an important sentence. Objects may appear rigid to us, but rigidity is often scale and circumstance pretending to be absolute. Now, Let us go deeper. Far beneath Earth's surface, pressure climbs steadily, because every layer of rock supports the weight of layers above it. By the time we reach the mantle and core, matter exists under conditions impossible at sea level. Minerals transform into denser crystal structures. Atoms rearrange into new packing patterns. What was stable near the surface becomes unstable below. Carbon, for example, under appropriate pressure and temperature can form diamond. Same element, different arrangement. Tighter bonding, greater hardness, considerably stronger opinions about cutting tools. This reveals one of pressure's favourite tricks. Pressure does not merely squash matter smaller, it can persuade matter to become something else. Atoms reorganize into forms that occupy less space or lower energy under those conditions. Pressure can rewrite architecture. Water does this too, though in especially theatrical fashion. Ice has multiple high-pressure forms beyond the familiar ice in your freezer. Under different pressures and temperatures, water molecules arrange into exotic crystal structures with names like Ice 6 or Ice 7. These likely exist deep inside icy moons and large planets. So somewhere in the solar system there may be strange forms of ice behaving nothing like cubes in lemonade. The universe refuses to be boring. Now move outward to giant planets such as Jupiter and Saturn. Beneath their cloud tops, pressure rises to astonishing levels. Hydrogen, normally a gas and famously lightweight, may enter a metallic state. Metallic hydrogen is thought to conduct electricity. It may help generate planetary magnetic fields. It is still hydrogen, but under pressure it behaves in ways no kitchen balloon could have predicted. This is the theme again. Pressure changes identity. Matter under enough squeezing becomes unfamiliar. And yet planets are still not the final masters of compression. For truly extreme pressure, we turn to stars. A star is a sphere of gas held together by gravity. That sentence sounds calm, but it hides violence. Gravity pulls inward from every direction. The enormous mass of the star presses down on deeper layers. Toward the center, pressure becomes immense. In the sun's core, temperatures reach millions of degrees, and pressure is high enough for hydrogen nuclei to fuse into helium. This fusion releases energy, creating outward pressure that balances gravity. The star survives because inward crushing and outward energy remain in tense cooperation. It is a long negotiation. But negotiations end. When a star exhausts usable fuel in its core, outward support weakens. Gravity notices immediately. The core begins to collapse. Now we arrive at the most dramatic use of pressure in the known universe. Gravity becomes not merely a force pulling things down, but a cosmic compressor. Imagine all the mass above the core pressing inward. Layers fall, density rises, temperature surges, electrons become crowded, atomic structures strain. The empty space inside matter starts disappearing. This is not poetic language. It is physical compression of atomic arrangements under overwhelming force. For stars with masses similar to the Sun, collapse may stop at the white dwarf stage. A white dwarf is the exposed stellar core left after outer layers drift away. It contains roughly the mass of the Sun packed into a volume similar to Earth's. Think carefully about that scale. The Sun could fit about 1.3 million Earth by volume. Compress roughly solar mass into Earth size and density rises enormously. Why does collapse stop there? Because of quantum mechanics. Electrons are fermions, particles that obey the Pauli exclusion principle. They resist being crowded into identical quantum states. This creates electron degeneracy pressure, a form of support not based on heat but on quantum rules. Matter gains a strange stiffness simply because particles refuse to overlap in forbidden ways. That means gravity can crush atoms dramatically, but eventually electrons push back through quantum behavior. White dwarf matter is unlike ordinary matter. Nuclei sit in a sea of highly compressed electrons. Familiar chemistry largely retires. A teaspoon of such material would weigh tons, and still gravity may ask for more. If the collapsing stellar core is massive enough, electron degeneracy pressure can fail. The inward squeeze becomes so severe that electrons combine with protons, producing neutrons and neutrinos. Atoms as atoms cease to exist. The empty spaces once defined by electron structure are gone. Matter is crushed beyond chemistry into neutron-rich form. This creates a neutron star. Now the pressure is almost beyond comfortable language. A neutron star may contain more mass than the Sun, in a sphere only around 20 kilometers across. City-sized, solar mass, same sentence. At these densities, a teaspoon of material would weigh billions of tons. The crust may contain bizarre compressed nuclear structures nicknamed nuclear pasta. Deeper layers may host superfluid neutrons or other exotic phases still debated. What stops collapse now? Neutron degeneracy pressure and strong nuclear interactions. Once again, quantum rules and particle forces resist further compression. The universe has layers of refusal. First atoms resist, then electrons resist, then neutrons resist. Gravity keeps asking. Nature keeps answering with new physics. If enough mass is present, even neutron star support may fail. Then collapse can continue toward black hole formation. At that stage, known descriptions become more uncertain. An event horizon forms. Beyond it, our current theories struggle to describe the final interior state completely. General relativity predicts a singularity. Quantum gravity likely has more to say, but has not yet delivered a finished manuscript. So pressure, followed to its extremes, becomes a journey through successive breakdowns of familiar structure. Molecules give way. Atomic spacing gives way. Electron-supported matter gives way. Neutron-supported matter may give way. Each threshold reveals a deeper layer of physical rules. This should also change how we think about hardness or strength. A diamond is hard because of atomic bonding. Steel is strong because of metallic structure and crystalline behavior. But neutron star matter is not stronger in the same everyday engineering sense. It exists under conditions maintained by immense gravity and quantum pressures. Remove a spoonful to your kitchen, if that were somehow possible, and you would no longer have a tidy spoonful for very long. Context matters. Pressure creates states that depend on pressure. That is true even in modest cases. Deep earth minerals may not remain stable at the surface. High-pressure ice forms melt or transform elsewhere. Materials carry passports stamped by environment. There is another subtle point worth noticing. Pressure depends not only on force but on area. High heels can dent floors more than broad shoes because the same weight is concentrated over smaller area. A knife cuts because force is focused at an edge. Snowshoes help because they spread weight across more surface. Gravity uses area cleverly too. As a star core shrinks, the same mass occupies smaller radius. Gravity at the surface intensifies. Compression accelerates. Smaller size can make collapse more severe. It is a feedback loop. Shrinking increases gravity's leverage. Gravity increases shrinking, until some new pressure source intervenes. This dance between compression and resistance shapes the life cycles of stars and the existence of compact objects. It also means the universe is not filled with one static kind of matter. Matter is adaptive under stress. Under low pressure, carbon may be soot. Under higher pressure, diamond. Hydrogen may be gas in a room, liquid in a laboratory, metallic in a giant planet. Stellar matter may be plasma, degenerate matter, neutron matter, or something stranger. The same fundamental particles can build very different worlds depending on the squeeze applied. There is something almost domestic about that. We too change under pressure, though hopefully with less neutrino emission. Now, if you look around the room you are in, nearly every object owes its shape to balanced forces resisting pressure. The chair supports weight through internal stresses. The floor spreads load into beams or concrete. Walls transfer forces downward. Your mattress compresses beneath you, then pushes back. Even the air pressing softly on your skin has pressure, though usually polite enough not to mention it. All structure is negotiation between load and resistance. The cosmos merely scales this principle upward until atoms themselves are called into emergency meetings. And that is why pressure is central to our larger question about the densest thing in the universe. Density is not only a property something has, it is often a property created. Matter becomes denser when circumstances force it to. Weight above, gravity inward, volume reduced, structure transformed. At some stage, collapse halts. At some stage, perhaps it does not. There are many ways to compress something. You can squeeze a sponge with your hand, you can pump air into a tire, you can stack books onto a cushion until the cushion develops opinions. You can place layers of rock atop other layers for millions of years and let geology handle the details. These are all familiar examples of pressure arriving from outside. A force is applied, matter responds, volume changes. But the universe has a more elegant and much more serious method. Sometimes matter compresses itself. This happens through gravity. Gravity is so familiar that it can seem almost too ordinary to deserve awe. We drop keys, we spill tea downward, we notice stairs, we complain about carrying groceries. It becomes background law, as taken for granted as daylight or the existence of spoons. Yet gravity is one of the great sculptors of cosmic structure. It gathers gas into stars, organizes planets into spheres, holds moons in orbit, bends light near massive objects, and, under the right conditions, crushes matter into forms no human hand could ever produce. Tonight we arrive at the moment when gravity stops being a quiet organizer and becomes an overwhelming compressor. To understand that transition, begin with something simple. Imagine a cloud of gas in space. It may be thin, cold, and spread over an enormous region. Such clouds, often made mostly of hydrogen, drift through galaxies for ages. They are not dramatic from the outside, they are patient. Then something disturbs the balance. A nearby supernova shockwave passes through. Two clouds collide. Galactic motion stirs the region. Slight clumps become slightly denser than their surroundings. Once a region becomes denser, its gravity strengthens. That stronger gravity pulls in more material. More material means more mass. More mass means stronger gravity. The process feeds itself. This is one of the universe's favourite patterns. Small imbalance becomes growing structure. Eventually the cloud contracts enough that particles collide more often. Temperature rises, the centre heats, pressure builds, a protostar is born. At first, gravity is doing the work. Matter falls inward, converting gravitational energy into heat. If enough mass gathers and the core becomes hot enough, hydrogen fusion begins. Now a star truly turns on. Fusion pushes outward. Gravity pulls inward. Balance returns, but now on a grander stage. This balance is called hydrostatic equilibrium, though that phrase sounds more like a premium mattress feature than a stellar condition. It means the inward crush of gravity is matched by outward pressure from hot gas and radiation produced in the core. As long as this balance holds, the star lives. For millions or billions of years, depending on mass, the star shines, because gravity is restrained by energy from fusion. That restraint matters more than it may first appear. A star is not just glowing gas. It is a vast object trying to collapse every second, prevented only by the energy released in its centre. Sunlight, in a sense, is part of the price paid to resist gravity. Our own sun is in this long stable phase. It has been balancing inward gravity and outward pressure for billions of years. Every sunrise represents another successful day of stellar negotiations. But gravity is patient. It does not tire. It does not become distracted. It waits for fuel to run low. Inside stars, fusion changes composition over time. Hydrogen becomes helium. In more massive stars, helium may fuse into carbon, oxygen, neon, silicon, and eventually iron. Each new stage is shorter than the last. The star's core becomes layered like an onion designed by thermonuclear engineers. Eventually a crucial limit is reached. Iron fusion does not release net energy the way lighter element fusion does. Instead of helping support the star, it becomes energetically costly. When a massive star builds an iron core, the support system begins to fail. Gravity notices immediately. Without enough outward pressure, the core collapses. This collapse can happen astonishingly fast. Matter that once resisted is suddenly falling inward. Electrons are squeezed into protons, producing neutrons and neutrinos. Outer layers crash inward and rebound in a supernova explosion. The star's envelope may be blasted into space. What remains is one of the densest objects in existence, a neutron star. This is gravity taking over completely, then being stopped only by deeper quantum forces. That phrase deserves a pause. In ordinary life, atoms define matter. Electrons orbit nuclei. Chemistry exists. Solids, liquids, gases, biology, coffee mugs, and furniture all depend on that arrangement. During core collapse, gravity crushes matter so intensely that atomic structure fails. Electrons are forced into nuclei. The spacious architecture of atoms disappears. Matter becomes neutron-rich and packed at nuclear densities. A star that may once have been larger than our Sun leaves behind an object only around 20 kilometers across, city-sized, yet containing more mass than the Sun. This is what happens when gravity takes charge. It converts scale into density. The result can spin rapidly, emit beams of radiation, and possess magnetic fields so strong they stretch imagination before breakfast. We call some of these objects pulsars because their beams sweep past Earth like lighthouse flashes. But gravity can go further. If the collapsing core is massive enough, even neutron pressure may not halt the inward fall. Then no known force stops collapse before an event horizon forms. A black hole is born. Here gravity does not merely compress matter, it alters space-time so strongly that escape becomes impossible once the horizon is crossed. This is why the birth of extreme density is really the story of support systems failing one by one. First, ordinary gas pressure balances gravity in a living star. When fuel runs low, thermal support weakens. Electron degeneracy pressure may stop collapse, creating a white dwarf. If mass is greater, electron support fails. Neutron degeneracy pressure may halt collapse, creating a neutron star. If mass is greater still, even that may fail. Black hole formation follows. Each stage is gravity pressing deeper into the structure of matter. It is like descending floors in a building where every lower level reveals more fundamental rules. Now, one might ask why gravity, the weakest of the fundamental forces on particle scales, becomes so dominant in stars. Excellent question. Between two tiny particles, gravity is indeed extremely weak compared with the electromagnetism. A small refrigerator magnet defeats the gravitational pull of the entire Earth on a paperclip. And yet gravity has two enormous advantages. First, it is always attractive. It only pulls together. Electromagnetic forces can attract or repel, often cancelling out in bulk matter. Second, gravity acts on mass energy universally. Every bit of matter contributes. So while weak individually, gravity accumulates relentlessly when enough mass gathers. Stars contain enormous amounts of mass. Planets do too, though not enough to ignite fusion. Galaxies gather even more. Once matter is abundant, gravity becomes king through sheer persistence. This accumulation explains why spherical shapes are common in large objects. Small asteroids can remain irregular because their self-gravity is weak. Larger bodies become round because gravity pulls high regions downward and fills low regions until a sphere, the most efficient shape under self-attraction, emerges. Scale invites gravity to dominate. Then there is the strange relationship between shrinking and pressure. When an object contracts under gravity, its central pressure rises because the overlying weight is concentrated into smaller radii. Gravity's grip intensifies as the object becomes more compact. This can trigger runaway collapse unless something new resists. That is why stellar endings are dramatic. Compression strengthens the very force causing compression. It is a feedback loop with catastrophic tendencies. Still, not every star dies violently. Low and medium mass stars, including our Sun, eventually shed outer layers and leave white dwarfs. No spectacular supernova is required. More of a dignified retirement with glowing consequences. Massive stars, however, live faster and end harder. They burn fuel quickly, evolve through heavier elements, and can collapse into neutron stars or black holes. Mass decides. Fate. This is one of the simplest and most powerful truths in stellar evolution. Give a star more mass, and gravity writes a different ending. There is also beauty in how the universe recycles these endings. Supernova explosions scatter heavy elements into space. Carbon, oxygen, silicon, calcium, iron, and many others are forged in stars and distributed through violent deaths. Planets form from enriched debris. Bodies form on planets. Bones use calcium forged in ancient stars. Blood carries iron born in stellar furnaces. So gravity's destructive finales are also creative events. It crushes stars, then seeds galaxies. That dual role is worth noticing. Gravity builds by breaking. Now let us bring this closer to the question of density. Why does gravity create such extreme density rather than merely making large, heavy objects? Because gravity acts inward on every part of a massive body simultaneously. A mountain rests on the ground. Much of its weight is supported externally by Earth. A star floats in space. Its own layers support layers above through internal pressure. There is no table beneath it. Everything must hold itself up. That self-support grows harder as mass increases. The center bears the weight of all outer layers. In giant stars, the burden becomes immense. When fusion can no longer help, the center loses the argument quickly. Collapse follows, and collapse means smaller volume with similar mass. Density surges. A white dwarf packs stellar mass into planetary size. A neutron star packs stellar mass into city size. A black hole packs enough mass into a region whose escape speed exceeds light. This is compression beyond anything chemistry or engineering could imitate. No machine humans can build can reproduce those global self-gravitating conditions on macroscopic scales. Only stars and their deaths perform this craft naturally. Even planets hint at the process. Jupiter is far more massive than Earth, yet not proportionally larger. Add mass to gas giants and gravity compresses them, limiting size increase. Some exoplanets with greater mass than Jupiter are similar in radius or even smaller. More mass can mean more compression rather than more width. Gravity prefers compactness when allowed. There is also a philosophical calm in this story. The same force that makes apples fall and keeps your feet on the floor also shapes neutron stars and black holes. It operates continuously across scales: kitchen gravity, planet gravity, star gravity, galaxy gravity. One rule, many consequences. That continuity is deeply satisfying. No hidden cosmic switch flips at large sizes. The same interaction simply gains influence when enough matter gathers. Not every star ends its life in an explosion. This may come as a relief to the star, though we have no evidence stars experience anxiety about career transitions. Many do not become supernovae, do not collapse into black holes, and do not spend their final moments tearing the surrounding cosmos apart in dramatic fashion. Some simply shrink. That sounds modest, almost polite. A star that once blazed for billions of years quietly contracts into something small, hot, dense, and stubbornly persistent. These remnants are called white dwarfs. The name has a curious gentleness to it. Considering what the object actually is, it sounds like it should live in a cottage and offer practical advice. In reality, a white dwarf is the exposed core of a dead star, containing a mass comparable to the Sun packed into a volume similar to Earth. That is not cottage behaviour. To understand how such an object forms, let us begin with a star like our Sun. For most of its life, A sun-like star is balanced. Gravity pulls inward. Pressure from the hot core and energy from nuclear fusion push outward. This long truce can last billions of years. The star shines steadily, warms planets, supports weather systems, and gives life a chance to develop hobbies. But hydrogen fuel in the core is finite. Eventually the central hydrogen becomes depleted. Fusion there slows. Without enough outward pressure, gravity begins to compress the core. Compression heats surrounding layers, and hydrogen fusion shifts into shells around the contracting center. The outer atmosphere expands enormously. The star swells into a red giant. If our sun were in that stage today, it would become vastly larger than now. Inner planets would have an unpleasant time. Red giants are strange objects. Their outer layers are puffed up and diffuse, while their cores become compact and hotter. A star can grow larger while preparing to become smaller. This is classic stellar behavior, complicated, elegant, and mildly contradictory. As the red giant evolves, helium fusion may begin in the core, producing heavier elements such as carbon and oxygen, but for stars with masses like the Sun, the temperatures and pressures never become sufficient to fuse much heavier material all the way toward iron. Instead, the star reaches a practical limit. Its outer layers become unstable and are gradually cast off into space, forming a glowing shell of gas called a planetary nebula. The name is historical and misleading. It has nothing to do with planets. Astronomy has many strengths, but naming conventions occasionally wander. What remains after those layers drift away is the hot central core. This core is the white dwarf. The first thing to appreciate is scale. The Sun is enormous. Roughly 1.3 million Earths could fit inside it by volume. Yet the white dwarf left behind may be only about the size of Earth. So a star that once spanned hundreds of thousands of kilometers across ends as an object closer in size to a planet. Same broad amount of mass, much smaller space, immense density. A teaspoon of white dwarf matter would weigh tons on Earth. Different estimates vary depending on composition and exact conditions, but all agree on the central point. Do not spill it on the carpet. How can matter be compressed so much without continuing to collapse forever? This is where physics changes tone. Ordinary stars are supported by thermal pressure from hot gas and fusion energy. White dwarfs are supported by something stranger: electron degeneracy pressure. The phrase sounds like a courtroom accusation, but it refers to a quantum mechanical effect. Electrons are fermions, and fermions obey the Pauli exclusion principle. Two identical fermions cannot occupy the same quantum state in the same way. As gravity squeezes matter tighter, electrons are forced into a smaller volume. Available quantum states fill up. Further compression requires electrons to occupy higher momentum states. This creates a pressure that does not rely on heat. Even a cooling white dwarf remains supported. That is remarkable. A normal star needs fusion to avoid collapse. A white dwarf does not. It resists gravity through quantum rules alone. The star has shut down its main furnace, yet still refuses to vanish, hence tonight's title. This resistance makes white dwarfs one of the clearest examples of quantum mechanics shaping astrophysical reality on a macroscopic scale. Tiny particle laws determine the fate of an object with planetary size and stellar mass. The universe enjoys linking the microscopic and the gigantic. White dwarfs are also extremely hot when first formed. Their surfaces can exceed 100,000 degrees Celsius. They glow white or bluish-white, which inspired the name, but they no longer generate major internal energy through sustained fusion. Over immense spans of time, they simply radiate stored heat away and cool gradually. This cooling takes billions, then trillions of years. In fact, the universe is not old enough for any white dwarf to have fully cooled into its hypothetical final state, sometimes called a black dwarf. No black dwarfs are expected to exist yet because not enough time has passed since the Big Bang. There are cosmic processes so slow that reality itself has not finished demonstrating them. White dwarfs therefore remain warm embers of ancient stars, slowly fading but still present. Let us consider their composition. Many white dwarfs are made mostly of carbon and oxygen, produced in earlier fusion stages. Others, especially from lower mass progenitors, may contain more helium. More massive precursors can leave oxygen neon magnesium cores. So although we group them under one name, white dwarfs are a family of stellar remnants with varied internal recipes. Still, none of these recipes resemble everyday chemistry. At the densities involved, atoms are crushed close together. Nuclei sit in a sea of highly compressed electrons. Matter behaves as degenerate matter, not ordinary solid, liquid, or gas. You would not mistake it for marble. You would also not get the chance. Now imagine standing near a white dwarf, if standing nearby were somehow practical and survivable. Its gravity at the surface would be intense. A person weighing 70 kilograms on Earth would effectively feel vastly heavier there, though many other hazards would become urgent first. Its escape velocity is thousands of kilometers per second. Its atmosphere, if present, may be only a thin outer layer of hydrogen or helium atop the compact core. Its size is small by stellar standards, yet it can contain about half the Sun's mass or more. This combination of small radius and large mass makes white dwarfs powerful laboratories for physics. They also help to confirm relativity. Light escaping strong gravity loses energy, shifting toward longer wavelengths. This gravitational redshift was measured in white dwarf spectra, providing evidence for Einstein's predictions. Even in retirement, these stars contribute academically. There is another curious rule governing white dwarfs. Unlike many everyday objects, adding more mass can make a white dwarf smaller. This sounds backward because we're used to larger things often becoming larger when more material is added. Add more dough, get more bread. Add more books, regret follows. But in white dwarfs, stronger gravity from added mass compresses the star further. Electron degeneracy pressure resists collapse, but the object becomes more compact. More mass. Smaller radius. Physics can be wonderfully impolite to intuition. This trend cannot continue forever. There is an upper mass limit called the Chandrasekhar limit, around 1.4 times the mass of the Sun, depending on details. Above this, electron degeneracy pressure is no longer sufficient to support the star. Subramanian Chandrasekhar calculated this while still young, revealing that white dwarfs have a maximum stable mass. At first, some senior figures resisted the conclusion. Science, like family dinners, sometimes contains awkward moments before acceptance, yet the mathematics held. Beyond that limit, collapse must continue, potentially leading to neutron star formation, or other violent outcomes depending on circumstances. This makes white dwarfs stable only within bounds. They are stubborn, but not invincible. White dwarfs also play starring roles in binary star systems. If a white dwarf orbits a companion star closely enough, it may pull gas from that companion. Material accumulates on the white dwarf's surface. Under certain conditions, runaway fusion ignites in the accreted layer, causing a nova. The white dwarf survives but flares dramatically. In other cases, continued mass gain may push the white dwarf near the Chandrasekhar limit, triggering a Type 1a supernova. The star can be disrupted entirely in a thermonuclear explosion. These events are so bright they can outshine whole galaxies temporarily and have been used as standardizable candles to measure cosmic distances. So one of astronomy's best tools for mapping the expanding universe comes from dead stars flirting with instability. White dwarfs continue to be useful. Let us bring this closer to home. Our Sun is expected to become a white dwarf someday, billions of years from now. It will pass through red giant stages, shed outer layers, and leave behind a dense remnant about Earth-sized. No human calendars need immediate adjustment. The timeline is comfortably remote. Still, it means that the final form of the star that nourishes present life is not endless brilliance, but compact persistence. That idea has a certain dignity. The sun will not explode into a supernova. It lacks the mass. It will contract, glow, cool, and remain. White dwarfs are common throughout the galaxy because many stars fall into the mass range that produces them. Since smaller stars live long lives, the Milky Way likely contains vast numbers of white dwarfs, many faint and ancient. The night sky may be populated with stellar cores quietly cooling in darkness, former suns reduced in size but not erased. There is something deeply instructive in them. They show that endings need not be explosive to be profound. They show that pressure can transform matter into new states. They show quantum mechanics holding up a star. They show that size alone tells us little about importance. An Earth-sized object can contain solar mass. A fading ember can preserve the memory of a star. And they show that gravity, though powerful, does not always win outright. Sometimes it is halted by rules written into the behaviour of electrons. That pause in collapse creates one of the densest stable objects we know, without crossing into even stranger territory. Because white dwarfs are not the final stop on the road to extreme density. They are the first great barrier. There is a common image of gravity in the mind. Gravity pulls. It drags things downward, gathers clouds into stars, keeps planets in orbit, drops toast with suspicious consistency, and generally behaves like the universe prefers everything closer together than we do. That image is correct as far as it goes. But it leaves out something equally important. Nature resists. Matter does not simply collapse whenever gravity asks. It pushes back in different ways depending on the circumstances. Gas pressure can resist. Radiation can resist. Structural strength can resist for a while. Quantum mechanics, when conditions become extreme, can resist in ways that feel almost impossible until you understand the rules. Tonight, we arrive at the first great quantum barrier against gravitational collapse, electron degeneracy pressure. It sounds technical, perhaps even stern, but it describes one of the strangest and most beautiful acts of resistance in the cosmos. A dead star, no longer powered by fusion, can remain standing because electrons refuse to be crowded beyond certain limits. That sentence would have sounded unlikely in most centuries. To see why it matters, let us begin with ordinary pressure. Imagine air trapped in a balloon. Molecules zip around randomly, colliding with the balloon's inner surface. Those countless collisions create pressure outward. If the balloon is squeezed, molecules strike walls more often and pressure rises. This is familiar thermal pressure. Heat gives particles motion. Motion creates support. Stars use a grand version of this principle. In a normal star like the Sun, the hot plasma in the core pushes outward while gravity pulls inward. Fusion reactions keep temperatures high enough for this outward pressure to continue. As long as fuel lasts, balance survives. But when a Sun-like star exhausts core fuel, things change. Fusion weakens, outward thermal support declines, gravity begins compressing the core. If ordinary gas pressure were the only defense, collapse would continue far deeper than it actually does. Yet many stars do not collapse into neutron stars or black holes. They stop at the white dwarf stage. Why? Because another kind of pressure appears, one not powered by heat. To understand it, we need electrons. Electrons are members of a class of particles called fermions. Protons and neutrons are fermions too. Fermions obey one of the foundational rules of quantum physics, the Pauli exclusion principle. This principle states that identical fermions cannot occupy the same quantum state in the same system. In everyday language, no two identical electrons can simply pile into the exact same available seat. Quantum nature enforces spacing. Now, this is not spacing in the sense of tiny chairs arranged in rows. It concerns allowed energy states, momentum states, and wave behaviour. But the metaphor of seating is useful enough to begin. Imagine a theatre with assigned seats. If a few people enter, they choose the easier spots. Plenty of room remains, no problem. As more people arrive, the best seats fill. New arrivals must occupy less convenient positions farther away or higher up. Eventually the theatre is full. Additional arrivals cannot all sit in the same prime seat because the rules forbid it. Now replace theatergoers with electrons and seats with quantum states. As matter is compressed, electrons are forced into a smaller volume. The number of available low-energy states becomes limited. More and more electrons must occupy higher energy states. That crowding generates pressure, not because electrons are hot, not because they're bouncing randomly like gas molecules, because quantum rules forbid excessive overlap. This is electron degeneracy pressure. It is one of the universe's most elegant refusals. Even if a white dwarf cools significantly, this pressure remains. That is what makes it so different from ordinary thermal support. A hot gas cools and loses pressure. Degenerate electrons keep resisting because the exclusion principle does not care about temperature in the same way. The star can go dark slowly and still remain structurally supported. That is extraordinary. A stellar remnant survives because microscopic particles obey bookkeeping rules with cosmic consequences. Now let us picture the formation more clearly. A sun-like star ages. Its outer layers drift away. The core contracts under gravity. Atoms are pushed closer together. Electrons become increasingly confined. At first, ordinary matter responds much as compressed matter does elsewhere. Then the densities rise high enough that electron quantum states become packed tightly. The electrons are said to become degenerate. Once this regime dominates, further compression becomes increasingly difficult. Gravity pushes inward. Electron degeneracy pushes outward. Balance is restored. The result is a white dwarf, about the mass of the sun, about the size of Earth, supported not by fire but by quantum mechanics. This is why white dwarfs are often described as dead stars that still stand upright. They are stellar cores held up by a rule of identity. There is another subtle and fascinating consequence. In ordinary materials, heating often causes expansion. Cooling often causes contraction. White dwarfs do not behave in such simple ways, because degeneracy pressure does not depend primarily on heat. Cooling changes brightness and temperature, but the core remains supported. A white dwarf can cool for billions of years without dramatically collapsing further. It is less like a dying ember shrinking into ash, and more like a hot metal sphere slowly radiating heat, while its structure remains set by deeper physics. Now, one may ask whether electrons are literally pressing outward like tiny springs. Not exactly. Pressure in physics can arise from many sources. It need not mean particles with elbows shoving neighbours. In this case, confinement forces electrons into higher momentum states. That momentum distribution creates measurable pressure. Quantum systems can resist compression simply through a loud state structure. This is one of those moments where everyday language strains slightly under the weight of reality. Still, the outcome is clear enough. Compress enough electrons into a small enough space, and they fight back. White dwarfs reveal this beautifully. A teaspoon of white dwarf matter would weigh tons, yet despite that density, the star does not continue collapsing under its own gravity, because degenerate electrons provide support. Gravity meets its first major wall, but it is not an infinite wall. There is a limit. If enough mass is added to a white dwarf, gravity strengthens further. The electrons are forced into ever more energetic states, moving at speeds approaching the speed of light. Their pressure response changes. Eventually, electron degeneracy can no longer hold the star up. This threshold is known as the Chandrasekhar limit, around 1.4 solar masses, depending on composition. Below it, white dwarfs can be stable. Above it, collapse resumes. That discovery was one of the great triumphs of theoretical astrophysics. It showed that even quantum resistance has bounds. Gravity can be delayed. It cannot always be denied. If a white dwarf in a binary system steals gas from a nearby companion, it may creep toward this limit. Sometimes the result is a Type 1a supernova, a thermonuclear explosion so bright it can rival galaxies. Sometimes collapse may proceed toward neutron star formation, under different circumstances. Either way, the first wall has been breached. Before we move on, let's appreciate how counterintuitive this all is. In daily life, pressure comes from heat, springs, compression of materials, or structural supports. A chair supports you because wood or metal resists bending. A tyre supports a car because pressurized air pushes outward. A boiler supports internal force through hot gas pressure. But a white dwarf supports stellar mass because electrons are not allowed to share quantum states too freely. That is a profoundly different category of support. It reminds us that the universe at large scales is built from rules operating at tiny scales. Stars are not separate from particle physics. They are particle physics with gravity added and volume turned up enormously. There is something quietly humbling in that. The fate of a star can depend on the statistical arrangement of electrons. The glow of galaxies can depend on exclusion principles. A cosmic object visible across light years may be standing because of mathematics first glimpsed in quantum theory. Now consider what the inside of a white dwarf might be like. There is no ordinary crystal floor one could stand upon. Matter is compressed into nuclei immersed in a sea of degenerate electrons. The outer layers may be thin atmospheres of hydrogen or helium, but beneath lies exotic, dense matter unlike anything naturally present on Earth. Surface gravity is intense, escape velocity is immense. The star may be roughly Earth-sized, yet with half the Sun's mass or more. It is compactness made real, and still, in the hierarchy of dense objects, it is only an early stage. That is worth emphasizing. White dwarfs are astonishing by human standards, yet compared with the neutron stars, they are spacious. Compared with black holes, they are practically conservative, which means electron degeneracy is powerful, but not final. Nature has deeper levels of resistance waiting below. If gravity overcomes electron support, electrons can combine with protons to form neutrons. Atoms disappear as familiar entities. Matter enters a new regime where another quantum barrier emerges, neutron degeneracy pressure, the second wall. But before descending there, pause with the first one. A white dwarf is what remains when a star runs out of fire yet still refuses collapse. It is supported by particles that cannot be stacked carelessly. It glows not from fresh fuel, but stored heat. It persists for ages because quantum law says no. That quiet no is one of the most consequential words in the universe. Without it, many stars would collapse further. White dwarfs would not exist. Supernova pathways would differ, stellar populations would change, cosmic history itself would look different. So when we speak of density and the forces that shape it, we should remember that gravity is only half the story. The other half is resistance. A white dwarf is already a startling object. It contains stellar mass in planetary size. It is supported not by fire, but by quantum rules. It glows quietly while cooling over billions of years. By any reasonable standard, that should be enough strangeness for one category of object. The universe disagrees, because there are stars born heavy enough that electron degeneracy pressure, impressive though it is, cannot provide the final answer. Gravity presses harder. The first wall of resistance fails. Matter is driven beyond the familiar architecture of atoms, and when that happens, something smaller, denser, and far more severe can be born. A neutron star. The name sounds tidy, almost modest. It does not adequately prepare anyone for what it describes. A neutron star is the collapsed core left behind after certain massive stars die in catastrophic fashion. It may contain more mass than the Sun, yet fit inside a sphere only around 20 kilometers across, not 20,000. 20. A city-sized object with stellar mass. That sentence remains strange no matter how many times it is read. To understand how such a thing forms, let us begin with the life of a massive star. Massive stars burn through fuel quickly. Their cores reach higher temperatures than stars like the Sun and can fuse heavier and heavier elements in stages. Hydrogen to helium, helium to carbon, carbon onward through successive steps until the core builds iron. Iron is a turning point. Fusion of lighter elements tends to release energy that helps support the star against gravity. Iron does not cooperate in the same way. Fusing iron consumes energy rather than supplying it. The star's central business model begins to fail. Without sufficient outward support, gravity gains the advantage immediately. The iron core collapses in a fraction of a second. Densities soar, temperatures rise, electrons are crushed into protons. This reaction creates neutrons and neutrinos. The basic equation in simplified form is proton plus electron yields neutron plus neutrino. The neutrinos stream outward in colossal numbers. Outer layers crash inward, then rebound in a violent supernova explosion. The star's outer body may be blasted into space, enriching the galaxy with heavy elements. What remains at the centre can be a neutron star. This is the moment matter crosses a profound boundary. In everyday objects, atoms define structure. Nuclei sit at the centre. Electrons occupy surrounding quantum states. Chemistry exists because electrons bind atoms into molecules. In a neutron star, that familiar arrangement largely ends. Electrons have been forced into protons. Separate atoms, as ordinary entities, no longer dominate the interior. Matter collapses beyond atoms. That phrase is not poetic exaggeration. It is literal in physical terms. The roomy spacing of atomic structure is gone. Gravity has crushed matter to densities comparable to atomic nuclei themselves. If white dwarfs compress atoms dramatically, neutron stars go further and erase their ordinary identity. Now imagine scale again. Take more mass than the Sun. Compress it into an object about the width of a city. That is enough density to make earthly language nervous. A teaspoon of neutron star matter would weigh billions of tons. Exact numbers depend on conditions and whose teaspoon is being volunteered, but the conclusion remains firm. You would not be stirring tea with it. Neutron stars are often around 10 to 20 kilometers in radius, though measurements vary. Their masses commonly range around 1.1 to over 2 times the mass of the Sun. This means surface gravity is staggering. If you dropped an object from 1 meter above a neutron star's surface, several other issues would become urgent before impact, but the acceleration would be extraordinary. Escape velocity becomes a substantial fraction of the speed of light. Time itself runs more slowly there relative to distant observers due to strong gravity. Relativity is no longer optional background theory. It becomes daily operating procedure. What holds a neutron star up? The answer is more subtle than it is made of neutrons. Gravity wants continued collapse. What resists is neutron degeneracy pressure, along with strong nuclear interactions between particles packed at extreme density. Neutrons are also fermions. They obey exclusion rules similar in spirit to electrons. They cannot all occupy the same quantum states carelessly. As gravity squeezes harder, momentum states fill and pressure rises. Once again, quantum mechanics become structural engineering. But the environment is harsher now. This is the second wall of resistance. The first wall, electrons, failed. The second wall uses neutrons. There is something almost architectural in this layered descent. Ordinary matter, white dwarf matter, neutron matter. Each deeper level appears only after the one above can no longer bear the load. Now, what is a neutron star actually like inside? That is one of the great active questions in astrophysics. We know the outer crust likely contains nuclei packed in a lattice, with free electrons moving among them. Deeper down, nuclei become increasingly neutron-rich. Eventually they may dissolve into a fluid dominated by neutrons. Between these layers may exist bizarre transitional structures nicknamed nuclear pasta. Yes, really. Physicists use names like lasagna, spaghetti, and gnocchi-like phases to describe shapes matter may adopt when nuclear attraction and electric repulsion compete under immense density. This does not mean dinner is served. It means geometry becomes strange. Sheets, rods, tubes, bubbles, tangled forms. Matter organizes itself in the least inconvenient ways available. Still deeper inside, possibilities multiply. Perhaps superfluid neutrons flow without friction. Perhaps superconducting protons coexist. Perhaps quarks become partially deconfined. Perhaps entirely new phases await better theory and better observations. Neutron stars are not just dense objects, they are laboratories nature built before humans learned to write. Now consider rotation. When a star collapses from a large radius to a tiny one, angular momentum is conserved. This is the same principle that makes a figure skater spin faster when pulling arms inward. So neutron stars can rotate astonishingly quickly. Some spin many times per second. Some rotate hundreds of times each second. These rapidly spinning neutron stars, especially when emitting beams of radiation from magnetic poles, are observed as pulsars. The beam sweeps past Earth regularly, producing pulses more precise than many clocks. A dead star, crushed beyond atoms, can become one of the most accurate timing devices in the galaxy. Again, the universe overachieves. Then there are magnetars. These are neutron stars with magnetic fields so intense they exceed ordinary imagination. Their fields can be trillions of times stronger than Earth's. At close range, such fields would distort atoms, damage electronics, and render many practical concerns obsolete. Occasionally, magnetars release bursts of high-energy radiation detectable across vast distances. Compactness, gravity, speed, and magnetism often travel together. What would happen if you approached one? First, approach is not recommended. Second, tidal forces near the surface would be severe. Gravity changes rapidly over short distances because the object is so compact. A person would experience different pulls between feet and head large enough to end the conversation. Third, the surface environment may include intense radiation and magnetic effects. Fourth, you would have made several poor planning choices. Even standing 1 meter taller on a neutron star would matter measurably. Gravity gradients are that steep. Now let us compare with white dwarfs. White dwarfs are Earth-sized remnants supported by electrons. Neutron stars are city-sized remnants supported by neutrons. White dwarfs may contain about 0.6 solar masses commonly. Neutron stars commonly exceed a solar mass. White dwarfs are extraordinary. Neutron stars are white dwarfs after gravity has dismissed subtlety. And yet even neutron stars may not be final. There appears to be an upper mass limit. Add enough mass, perhaps by merger or accretion, and neutron support may fail too. Collapse may continue toward black hole formation, so neutron stars are both endpoint and threshold depending on mass. They mark the deepest stable matter we have strong evidence for, yet not necessarily the end of compression. Observationally, neutron stars are immensely valuable. When two neutron stars orbit each other, they lose energy through gravitational waves and spiral inward. Such mergers have now been detected. These collisions produce gravitational wave signals and electromagnetic aftermaths rich in heavy element production. Gold, platinum and other heavy elements may be forged in part through neutron star mergers. Jewelry owes some gratitude to catastrophic stellar remnants. The cosmos contains many such awkward origins. Neutron stars also help test fundamental physics. Their masses and radii constrain equations of state, relationships describing how matter behaves under extreme density. By measuring pulsars, timing binaries, X-ray bursts, and merger signals, scientists probe matter impossible to reproduce fully on Earth. We cannot build neutron stars in laboratories, so we observe the sky. There is also something philosophically striking here. A neutron star is what remains when gravity compresses matter so deeply that chemistry ends, atoms dissolve, and quantum statistics become bulk structure. The everyday world of wood, water, air, iron, skin, leaves, glass, and rain exists far above this regime, yet both worlds are made of the same fundamental ingredients arranged under different conditions. The spoon on your table and a neutron star differ not in belonging to separate universes, but in how matter is packed. That continuity is astonishing, Same laws, different pressure, different outcome. Tonight we have crossed beyond atoms. We have seen stars die, cores collapse, electrons merge with protons, and matter reborn as a compact sphere of neutrons. But numbers this extreme can remain abstract. Billions of tons per teaspoon is memorable, yet still difficult to feel. Numbers can be honest and still fail to communicate. That is one of the quiet difficulties of science. We can state a fact precisely, repeat it clearly, and remain nowhere near true understanding in the emotional sense. The sun is far away. Correct. The galaxy is large. Also correct. A neutron star is dense. Perfectly true, and almost useless without context. This is why people reach for comparisons. When discussing neutron stars, one phrase appears often. A teaspoon of neutron star matter would weigh billions of tons. It is dramatic, memorable, and slightly rude to teaspoons. Yet it persists because ordinary language needs help when confronting extreme density. Tonight, rather than rushing past that comparison, let us sit with it carefully. What does it actually mean for a spoonful of matter to weigh like a mountain? To begin, we should clarify something important. When scientists say a teaspoon of neutron star matter would weigh billions of tons on Earth, they're using the mass of that amount of matter and converting it into familiar terms. The spoonful itself is hypothetical. You're not visiting a neutron star with cutlery. This is fortunate. Still, the comparison points to real density. A typical teaspoon holds about 5 milliliters of volume. That is a small amount, enough for sugar, salt, medicine, honey, or the ambitious start of a recipe. It is something you can balance in one hand while making ordinary life decisions. Now imagine that tiny volume containing matter packed to neutron star densities. Instead of grains, liquid, or powder, it contains the equivalent mass of vast earthly objects. Different estimates vary depending on exact neutron star conditions, but values in the billions of tons are common. A spoonful the size of a casual kitchen measure, with mass comparable to mountains, ships, skyscrapers, or entire human-made districts. This is where the mind protests. Surely something so small should be light. But that protest comes from daily experience, where size and weight often correlate reasonably well. Large sofa, heavy. Small grape, light. Large truck, heavy. Small coin, light enough to loosen cushions. Neutron stars break that habit completely. They force us to separate size from mass. Volume tells us how much room something occupies. Mass tells us how much matter is there. Density tells us how astonishingly mismatched those two can become. Now let us build intuition step by step. Water has a density of about 1 gram per cubic centimetre. Conveniently, that means 1 milliliter of water has a mass of about 1 gram. 5 milliliters in a teaspoon, about 5 grams. Easy. Lead is much denser, roughly 11 times water. A teaspoon of lead would feel heavy for its size. Gold is denser still, around 19 times water. A teaspoon of gold would be substantial enough to inspire caution and perhaps several new friendships. But neutron star matter is not 10 times denser than water, not 100, not 1,000, not 1,000,000. It is around hundreds of trillions of times denser than water, depending on which region of the star we're discussing. This is not merely very dense. It is density so extreme that everyday scales stop being useful. If you compressed Mount Everest into something spoon-sized, you would at least be playing the right genre of imagination. Now, mountains themselves vary, and Everest is not a neat block one can weigh casually. But the comparison helps because mountains feel immovable. They represent mass on a human psychological scale. A teaspoon does not. Putting those together creates productive discomfort. Tiny object, mountain-like mass. That tension is the point. How can this happen? Because neutron star matter has largely bypassed atomic spacing. In ordinary matter, atoms contain tiny nuclei separated by electron structures that create familiar sizes. Solids feel packed, but on atomic scales they are roomy compared with nuclear matter. In a neutron star, gravity has crushed matter beyond ordinary atoms. Electrons have merged with protons. Matter is packed at densities closer to the nucleus itself. The empty space that makes everyday matter comparatively spacious has mostly vanished. This is the real source of the mountain teaspoon idea. Not magic. Not extra matter created from nowhere. Just familiar matter compressed beyond recognition. Let us compare with Earth. Earth's average density is about 5.5 grams per cubic centimetre. That is denser than water because rock and metal dominate. Even so, Earth as a whole is airy by neutron star standards. If Earth were somehow compressed to neutron star density while keeping the same mass, it would shrink dramatically. How dramatically? Roughly to a sphere only a few hundred meters across, depending on assumptions. A planet reduced to something the size of a hill or neighborhood-scale object. Same mass, tiny radius. That is what packing efficiency can do when atoms no longer run the show. Now let us compare with the Sun. The Sun contains about 333,000 Earth masses, yet a neutron star can contain more than a solar mass within a radius of roughly 10 to 12 kilometers. A star once larger than many planets combined becomes something you could cross by car if roads, survival, and every other relevant detail were somehow provided. This is why neutron stars are so hard to visualize. They combine incompatible categories: star mass, city size, nuclear density, surface gravity beyond ordinary intuition, rapid spin, sometimes lighthouse-like radio pulses. They feel invented, yet they are among the best supported objects in astrophysics. Now imagine trying to bring that teaspoonful to Earth. Again, impossible in practice, but useful conceptually. First, it would not remain a neat spoonful. Neutron star matter is stable because of immense gravity pressing inward. Remove it from that environment, and it would undergo violent decompression, rearrangement, and energetic consequences that would rapidly make the teaspoon itself irrelevant. This is worth emphasizing. The mountain-like spoonful exists meaningfully within neutron star conditions. It is not a collectible sample. Many extreme states of matter depend on context. Deep Earth minerals may transform at the surface. High-pressure ices melt or change. Neutron star matter taken away from neutron star gravity would not politely hold shape in your kitchen. The universe often says, conditions apply. Still, the comparison remains useful because it captures mass concentration. Another way to think about it is by people. Suppose an average person has a mass of around 70 kilograms. It takes many thousands of people to equal a modest ship, many more to equal a mountain-scale structure. Now imagine fitting the mass of enormous populations into a volume smaller than a sugar cube. That sounds absurd because it should. Neutron star density is absurd only by everyday standards, not by cosmic ones. Gravity, given enough mass, can be startlingly efficient. There is also a strange consequence of such density. Surface gravity becomes immense because a lot of mass sits very close to the center. Gravity depends on mass and distance. Reduce the radius drastically while keeping stellar mass, and the pull at the surface skyrockets. So the same compactness that makes the teaspoon comparison possible also creates gravitational conditions severe enough to bend light measurably and slow time relative to distant observers. Density and gravity become partners. Then there are collisions. If two ordinary rocks collide, they crack, chip, heat, scatter. If neutron stars merge, space-time itself ripples with gravitational waves. Heavy elements may be forged. Radiation flashes across space. Matter experiences conditions beyond laboratories. Again, city-sized objects with star mass change the scale of consequences. Now, one might ask whether all parts of a neutron star share identical density. No. Like Earth or the Sun, neutron stars have layers. The outer crust is less dense than the core, though less dense here still often means wildly dense by human standards. Deeper regions become more compressed. The core may host states of matter still uncertain. So when we cite teaspoon analogies, We are averaging or referencing characteristic densities, not claiming every cubic centimetre is identical. Reality prefers gradients. There is something psychologically useful in admitting this. Extreme facts often become slogans. Teaspoon equals mountain. Memorable? Yes. Complete? No. Better to hold both truths. The slogan helps imagination start. The details deepen it. Now let us place a teaspoon beside a mountain one final time. A mountain feels large because it occupies space dramatically. It towers, casts shadows, shapes weather, redirects rivers, and resists movement. A teaspoon feels trivial because it occupies little space and fits in a drawer. But mass does not care about symbolism. Matter packed tightly enough can hide enormous weight in tiny places. This is one of the great lessons of astrophysics. Appearance is negotiable. Structure matters more. The same lesson appears elsewhere in the cosmos. Red supergiant stars can be huge but relatively diffuse in outer layers. White dwarfs are small but heavy. Neutron stars are smaller still and heavier still per volume. The universe constantly warns us not to judge by size alone. There is also something calming in that. Important things are not always the loudest or largest. Power can be compact, meaning can be concentrated, weight can be hidden in quiet forms. Neutron stars embody that principle physically. They're not sprawling giants, they're condensed outcomes. A lifetime of stellar burning, followed by collapse, compressed into a compact remnant whose teaspoonful defeats metaphor. Tonight we have translated numbers into mountains, spoons, cities, and planets. We have tried to give the mind handholds on a cliff of scale, but density alone does not explain why neutron stars remain standing. Something must resist gravity even there. Atoms failed. Electrons failed. Yet collapse stopped. Gravity is persistent. That may be the simplest honest thing we can say about it. Gravity gathers dust into pebbles, pebbles into worlds, gas into stars, stars into galaxies, and if left unchecked, it keeps pressing inward with patient determination. It does not become bored. It does not get distracted. It does not decide things are compact enough and take the afternoon off. So far in our journey, we have watched matter resist in stages. Ordinary stars resist gravity through thermal pressure generated by fusion. White dwarfs resist through electron degeneracy pressure, where electrons refuse to be crowded into the same quantum states too freely. That first quantum wall can support stellar remnants of remarkable density. But for sufficiently massive collapsing cores, gravity pushes harder. The first wall fails. Electrons are forced into protons. Atoms lose their familiar identity. And then, under conditions so severe that daily language begins to wobble, a second barrier emerges. Neutron degeneracy pressure. This is one of the most extreme acts of resistance in the known universe. A dead star compressed beyond atoms can halt further collapse, because neutrons themselves obey quantum rules that refuse unlimited crowding. If electron degeneracy built the white dwarf, neutron degeneracy helps build the neutron star. To understand why, let us begin with the collapse of a massive star's core. When a massive star reaches the end of fusion support, gravity takes command quickly. The core contracts catastrophically. Densities rise. Electrons are squeezed into protons through inverse beta processes, producing neutrons and neutrinos. The neutrinos stream outward in astonishing numbers. Outer layers may explode in a supernova. At the center remains matter transformed. The roomy atomic structure of nuclei surrounded by electron clouds has largely ended. Instead of separate atoms defining the material, the interior becomes dominated by neutrons packed extraordinarily close together. Now we meet a natural question. Why do neutrons not simply collapse into an even tighter state immediately? The answer begins with the same quantum principle we met earlier. Neutrons are fermions. Like electrons, they obey the Pauli exclusion principle. Identical fermions cannot all occupy the same quantum state. So when gravity compresses neutrons into a smaller volume, available low-energy states fill. Additional neutrons must occupy higher momentum states. This generates pressure. Again, not pressure from heat, not pressure from little particles angrily elbowing each other. Pressure arising from the structure of allowed quantum states. This is neutron degeneracy pressure. If electron degeneracy was the first wall, neutron degeneracy is the second, and it stands much deeper in the hierarchy of collapse. There is something almost architectural about stellar death. Gravity descends level by level, and nature responds with deeper supports. Gas pressure, electron degeneracy, neutron degeneracy. Each appears when the previous support can no longer carry the load. But neutron stars are not held up by degeneracy pressure alone. At the densities involved, neutrons are close enough that the strong nuclear force also matters significantly. This force, which binds atomic nuclei together, behaves differently at different ranges. At very short distances, matter becomes increasingly resistant to compression. So the second barrier is really a partnership. Quantum exclusion plus nuclear interactions. Microscopic laws become macroscopic structure. A star survives as a compact remnant because particles obey rules discovered in laboratories and equations. This remains one of the most beautiful features of physics. The tiny governs the immense. Now let us compare scales. A white dwarf is about Earth-sized and supported by electrons. A neutron star is roughly city-sized and supported by neutrons. The difference is not merely more dense, it is matter entering a fundamentally deeper regime. In white dwarfs, atoms are crushed, but nuclei remain meaningful units embedded in degenerate electrons. In neutron stars, matter goes beyond ordinary nuclei across much of the interior. The atom as a familiar concept retires. This is why neutron stars feel so alien. They are not made of unusual ingredients. They are made of familiar ingredients under unfamiliar authority. Gravity changes context until matter changes category. What might the inside of such an object be like? The outer crust likely contains nuclei in a lattice with electrons flowing among them. Deeper down, nuclei become increasingly neutron-rich as pressure rises. Eventually, neutrons drip free from nuclei, forming a sea of particles around remaining nuclear structures. Go deeper still, and nuclei may dissolve entirely into dense nuclear matter dominated by neutrons, with some protons, electrons, and perhaps other particles mixed in. The core may host superfluids, superconducting components, hyperons, meson condensates, deconfined quarks, or states not yet fully understood. Scientists debate these possibilities actively because neutron star interiors are difficult to probe directly, which is an elegant understatement. We cannot open one, we cannot sample one. We infer their inner behavior through mass measurements, radii, spin rates, cooling patterns, X-ray signals, merger waves, and theory. The universe has hidden some of its best laboratories behind severe safety restrictions. Now, what does degeneracy pressure feel like in this context? Of course, no one is placing a hand inside a neutron star and reporting texture. But conceptually, imagine trying to force more neutrons into already crowded allowed states. As confinement increases, momentum requirements rise sharply. The system resists. It is as if matter says, there are no easy seats left. That metaphor served us with the electrons, and it still helps here, though the theatre has become much more intense. There is another important point. Neutron degeneracy pressure is stronger in the sense that it operates after far more extreme compression than electron degeneracy, but it is not limitless. There exists a maximum mass beyond which neutron star support may fail. The exact value depends on the equation of state, meaning how matter behaves at those densities, but observed neutron stars above 2 solar masses already constrain models. If enough mass accumulates, perhaps through merger or accretion from a companion star, gravity can overcome the second barrier too. Then collapse may continue into a black hole, so even this wall is mighty, not eternal. That gives neutron stars a special status. They are among the densest stable objects we know, balanced on the edge between persistence and disappearance. Not dead in the casual sense, not alive in the stellar sense, structurally surviving through quantum refusal. There is something deeply compelling in that image. Now let us discuss superfluidity briefly, because neutron stars seem unwilling to stop being interesting. Many models suggest that neutrons in parts of the interior can form a superfluid, a state in which matter flows with effectively zero viscosity under certain conditions. Protons may become superconducting. If true, the star's interior is not merely dense, but exhibits quantum collective behavior on enormous scales. This can affect rotation. Some neutron stars occasionally undergo glitches, sudden small increases in spin rate. One leading explanation involves interactions between the crust and superfluid interior transferring angular momentum. So a star remnant can hiccup rotationally because of quantum fluid dynamics inside a sphere of crushed matter. At this point, one begins to suspect the universe is showing off. There is also a lesson here about resistance itself. We often imagine strength as hardness, thickness, toughness, or visible solidity. But neutron star resistance is none of those in the ordinary sense. It is not a steel beam, it is not concrete, it is not diamond. It is a pressure emerging from identity rules and particle interactions. The strongest supports in nature are sometimes the least intuitive. That theme repeats elsewhere in science. Invisible magnetic fields steer plasma. Empty seeming vacuum hosts quantum fields. Tiny constants shape stars. Reality is under no obligation to resemble furniture. Now compare the second barrier to the first. Electron degeneracy appears when electrons are confined enough that quantum states crowd. Neutron degeneracy appears after collapse has gone much further, when neutrons dominate the matter. The first wall stops many stars. The second wall stops heavier remnants. Each barrier allows a new class of object to exist. Without electron degeneracy, white dwarfs vanish. Without neutron degeneracy and nuclear repulsion, neutron stars vanish. And if neutron stars vanished, much else would differ. Binary pulsars would not exist. Many heavy elements from mergers might form differently. Gravitational wave astronomy would have lost one of its grand spectacles. Some of the universe's most precise natural clocks would be absent. A great many scientific careers would need restructuring. So this quantum barrier matters beyond theoretical elegance. It shapes cosmic history. There is also something humbling in the scale transition. The exclusion principle was formulated to describe microscopic particles. Yet here it helps determine whether an object containing more than a sun's mass remains a neutron star or becomes a black hole. A rule for the very small influences the fate of the very large. That continuity is one of the deepest satisfactions in physics. Tonight we have descended past atoms, past electron support, into matter crowded enough that neutrons themselves bear the burden. Gravity presses inward from every direction. Quantum law and nuclear force answer back. The result is a city-sized sphere with stellar mass, stable for millions or billions of years. But stability does not mean stillness. Some objects in the universe announce themselves loudly. They explode, flare, collide, brighten or swallow nearby matter with dramatic appetite. Even from vast distances, they seem eager for attention. Astronomers appreciate this because the universe can otherwise be inconveniently dark. Other objects are more disciplined. They do not shout continuously. They pulse regularly, precisely, patiently, like a lighthouse sweeping across an ocean or a metronome placed inside a storm. These are pulsars. A pulsar is a rapidly rotating neutron star whose beams of radiation sweep through space. When one of those beams crosses Earth, we detect a pulse, then darkness, then another pulse, then another, repeating with astonishing reliability. At first discovery, the signals were so regular that some scientists briefly considered whether they might be artificial. This was not because astronomers are easily startled, but because nature had produced something that behaved uncannily like a cosmic transmitter. In the end, the explanation was even better. A dead star crushed beyond atoms, spinning in space, broadcasting time itself. To appreciate pulsars properly, we should begin with the object beneath the signal. A pulsar is a neutron star. That means it contains roughly stellar mass in a sphere only around 20 kilometers across. Matter has collapsed beyond ordinary atomic structure. Neutron degeneracy pressure and nuclear interactions resist further collapse. Surface gravity is immense, density is extreme, and yet despite all that heaviness and compression, many pulsars spin rapidly enough to embarrass household appliances. How does this happen? The answer is conservation of angular momentum. This principle appears in everyday life whenever a spinning figure skater pulls in their arms and rotates faster. The same total angular momentum is concentrated into a smaller radius, so spin increases. Now imagine not a skater, but a star. A normal star rotates. Perhaps slowly, perhaps moderately, but it turns. When its core collapses into a neutron star, the radius shrinks enormously. Something once hundreds of thousands of kilometers across may leave behind a remnant only tens of kilometers wide. That reduction in size is extraordinary. And when radius plummets, rotation can accelerate dramatically. A stellar core that once turned gently can become a compact object spinning many times each second. This is how pulsars are born fast. Some rotate once every few seconds, some many times per second. The fastest known millisecond pulsars spin hundreds of times each second. One full rotation can take less time than a blink. That means a city-sized sphere of ultra-dense matter can whirl faster than a blender while maintaining astrophysical dignity. Now, let us ask where the pulses come from. If pulsars were simply spinning hot balls, we would mostly see steady emission. Rotation alone does not create blinking. The key lies in magnetic fields. Neutron stars often possess strong magnetic fields. Very strong, sometimes unimaginably strong. Charged particles near these fields are accelerated and emit radiation. This radiation tends to emerge in beams from regions near the magnetic poles. Importantly, the magnetic axis is often tilted relative to the rotation axis, so as the neutron star spins, the beams sweep around like the light from a lighthouse. If Earth happens to lie in the path of one beam, we detect a pulse each time it swings past. Pulse, darkness, pulse again. The star is not turning on and off, we are simply intersecting the beam rhythmically. This geometric accident has made pulsars one of astronomy's great gifts. They are cosmic clocks. Many pulsars keep time with extraordinary precision. Their pulses arrive so regularly that small deviations can reveal subtle effects: orbital motion, gravitational waves, nearby companions, and even planets. Yes, planets. The first confirmed exoplanets were discovered around a pulsar in the early 1990s. This remains one of the universe's more unexpected combinations. Worlds orbiting the remnant of a dead, exploded star. Life, one suspects, would face branding challenges there. Still, the discovery showed how sensitive pulsar timing can be. Tiny shifts in pulse arrival times betrayed the gravitational tug of orbiting bodies. Imagine detecting planets by noticing slight lateness in the heartbeat of a collapsed star. Science can be wonderfully strange. Now let's return to the pulses themselves. Radio waves are the classic signature of many pulsars, but pulsars can emit across the electromagnetic spectrum, including visible light, X-rays, and gamma rays. The Crab pulsar, born from the supernova observed in 1054 CE, is famous for this. It sits in the Crab Nebula, spinning rapidly and powering energetic emissions that continue centuries after the original explosion. A star died. Its remnant still energizes the surrounding nebula. Endings in astronomy are often productive. Young pulsars are typically faster and more energetic. Over time, they lose rotational energy and gradually slow down. This is called spin down. The neutron star's rotation powers radiation and particle winds, draining energy little by little. Even so, little by little can last a very long time. These objects are efficient in a way most batteries would admire. Now consider the surface conditions of a pulsar. Gravity is immense, magnetic fields can be enormous, rotation can be rapid, matter is compressed beyond atoms. Time runs differently near such gravity than far away, and yet from far across space, what reaches us may be a calm, repeating pulse. This contrast is worth enjoying. Internal violence, external punctuality, like receiving polite postcards from a hurricane. There are also millisecond pulsars, which deserve special attention. These neutron stars spin hundreds of times per second and are often thought to have been recycled. In binary systems, a neutron star can accrete matter from a companion star. The infalling material transfers angular momentum, spinning the neutron star up over time. So an old pulsar can be re-energized by stellar companionship. The universe, even in extreme regimes, allows second acts. Millisecond pulsars are among the most precise clocks known in nature. Their stability makes them useful for experiments in fundamental physics. Arrays of pulsars across the sky are used in pulsar timing arrays to detect low-frequency gravitational waves. By monitoring tiny correlated changes in pulse arrival times, scientists can sense ripples in space-time caused by supermassive black hole binaries and other grand events. Think about that. Dead stars are helping us hear the slow tremors of the cosmos. A network of compact remnants serves as a galaxy-scale observatory. There is elegance in this arrangement no engineer would dare promise in advance. Pulsars have also tested general relativity powerfully. Binary pulsars, where two dense stars orbit each other, reveal orbital decay consistent with energy loss through gravitational radiation. This was one of the great early confirmations of Einstein's predictions. Again, precision emerges from extremity. The harsher the conditions, the cleaner some tests become. Now, what would it be like near a pulsar? As always, not recommended. If you stood near the surface, tidal forces, gravity and radiation would quickly end the sightseeing portion of the visit. A pulsar's magnetic environment can accelerate particles intensely. Its rotation can generate fierce electromagnetic effects. So while visually appealing from afar, proximity remains discouraged. Still, from safe distance, pulsars are among the most beautiful examples of order in nature. They remind us that chaos and regularity often coexist. A supernova explosion may create the neutron star. The remnant then spins with metronomic discipline. Violence gives way to rhythm. This happens elsewhere too. Galaxies born from turbulent history settle into spirals. Rivers carved by storms flow quietly afterward. Even lives shaped by upheaval can become steady. The universe repeats patterns in different languages. There is another subtle lesson in pulsars. We often imagine dead stars as gone, finished, inactive. Yet pulsars show that endings can remain dynamic for ages. A star may stop fusion and still continue affecting space around it through rotation, magnetic fields, particle winds, and precise pulses detectable across light years. Death in astronomy is frequently just a category change. Now let us place pulsars back into our larger question of density. Why do pulsars matter in a story about the densest things in the universe? Because they are not only neutron stars, but observable neutron stars with behavior we can track exquisitely. Their pulses allow measurements of mass, spin, magnetic field strength, orbital motion, and sometimes size constraints. They turn inaccessible dense matter into readable signals. Without pulsars, neutron stars would be far harder to study. With pulsars, dense matter sends data. That is a generous arrangement. Some neutron stars are impressive in the way mountains are impressive. They are massive, compact, stable, and quietly extreme. They spin, pulse, bend light, and contain matter packed beyond atoms, that would already secure a respectable place in the cosmic hall of unusual things. Then there are magnetars. Magnetars are what happen when a neutron star decides density alone is not enough, and adds a magnetic field so intense that normal comparisons begin to fail. They are among the most extreme known objects in the universe, not the most massive, not the largest, not the brightest all the time. But when it comes to magnetic intensity, magnetars sit in a category that feels almost impolite. To appreciate that, let us begin gently with magnetism itself. Magnets are familiar companions of ordinary life. They hold notes to refrigerators, guide compasses, secure cabinet doors, and occasionally disappear into drawers containing batteries, rubber bands, and mysteries. Earth itself has a magnetic field, generated largely by motions in its molten outer core. This field helps shield us from charged particles from the sun and guides migratory animals with enviable confidence. The sun also has magnetic fields, far more complex and dynamic than Earth's. Solar flares and sunspots are expressions of magnetic behavior in plasma. Even ordinary stars can host significant magnetic activity. But neutron stars take magnetism into a harsher realm. When a massive star collapses into a neutron star, its size shrinks enormously. If the original star possessed a magnetic field, the collapse can concentrate magnetic flux into a vastly smaller region. Imagine squeezing the field lines into tighter space while the star spins rapidly and conducts electricity extraordinarily well. The result can be a powerful magnetic field. Sometimes, in rare cases, the result is overwhelming. That is a magnetar. Typical neutron stars already possess strong magnetic fields. Magnetars exceed even those by large margins. Their surface fields can reach around 10 to the 14th to 10 to the 15th Gauss. Numbers like that are technically useful and emotionally useless without comparison. Earth's magnetic field near the surface is about half a Gauss. A common refrigerator magnet may be around 100 Gauss. Medical MRI machines operate in fields of a few tens of thousands of Gauss. A magnetar can exceed these by absurd factors. If Earth's field is a candle flame, a magnetar's is more like a starship engine someone forgot to regulate. This is why magnetars are often described as the strongest magnets known in the cosmos. Now, a natural question arises: how can a magnetic field matter so much? Because magnetic fields are not decorative. They influence charged particles, store energy, shape motion, and under extreme strengths can alter matter itself. Near a magnetar, the field is so intense that atoms behave differently. Electron structures can be distorted. Chemistry as we know it becomes unreliable. Materials would not simply sit there and remain politely themselves. At sufficient proximity, the field could induce electrical currents in conductors, disrupt electronics, and generally end modern convenience very quickly. Fortunately, known magnetars are not in the neighbourhood. This is a good example of distance being one of the universe's kindest inventions. So what creates a magnetar specifically, rather than an ordinary neutron star? The exact pathways are still studied, but leading ideas involve rapidly rotating newborn neutron stars with internal conditions that amplify magnetic fields through dynamo processes during formation. If the collapsing stellar core spins fast enough and convex strongly enough, enormous fields may be generated early in the object's life. In simpler terms, some stellar deaths are born with extra complications. Magnetars are also relatively young by astrophysical standards. Their intense magnetic fields gradually decay over time, releasing energy. That released magnetic energy powers much of their unusual behaviour. This makes them different from many pulsars, whose emissions are strongly tied to rotational energy. A magnetar can shine, flare and erupt because its magnetic field is unwinding and reorganising. Imagine a coiled spring made of invisible force, under tremendous stress, slowly cracking and releasing stored energy. That image is not exact physics, but it points in the right direction. Now let us discuss what magnetars actually do. They flare. Sometimes modestly by cosmic standards, which still means impressively by human standards. Sometimes violently. Their crusts, thin rigid outer layers over ultra-dense interiors, may experience stresses caused by magnetic distortion. When those stresses exceed what the crust can bear, starquakes can occur. Yes, starquakes. The crust of a neutron star can crack and shift, releasing bursts of X-rays and gamma rays. Earth has earthquakes. Magnetars have crustal failures on objects made of matter beyond atoms. Again, the universe declines moderation. These bursts can be brief but powerful. In especially dramatic cases, giant flares release astonishing amounts of energy in fractions of a second. One famous event occurred in 2004 from the magnetar SGR 1806-20. The burst was so intense that it affected Earth's upper atmosphere despite originating tens of thousands of light years away. That is an impressive level of remote inconvenience. Imagine an event across the galaxy disturbing your planet's environment because a dead star's magnetic field had a bad afternoon. Magnetars are often observed as soft gamma repeaters or anomalous X-ray pulsars, historical categories based on how they were first detected. Over time, these classes came to be understood largely as manifestations of magnetar behavior. Science names first, organizers later. Now consider the object itself beneath the drama. A magnetar is still a neutron star. It remains roughly city-sized. It still contains more mass than the Sun, compressed into a sphere only around 20 kilometers across. Surface gravity remains immense. Density remains extreme. What changes is the magnetic field and the energy budget that field provides. So if a pulsar is a precision lighthouse, a magnetar is more like a lighthouse built inside a thunderstorm, with the lamp occasionally exploding. This is not an official classification, but it is emotionally accurate. How close would you need to be for danger? Closer than one should ever attempt. Popular science often mentions that a magnetar passing within a modest, astronomical distance could disrupt electronics or damage living tissue through intense radiation and magnetic effects. Exact outcomes depend on many factors, but the broad principle is clear. These are not picnic objects. Even from afar, their bursts can be detectable across galaxies in some cases. Yet despite their violence, magnetars are scientifically precious. They allow us to study matter under extreme magnetic fields impossible to reproduce fully on Earth. They help test theories of neutron star crusts, superdense interiors, radiation processes, and quantum electrodynamics in intense field regimes. In such fields, even the vacuum of space may behave in subtle, non-linear ways. Light propagation can be affected through phenomena like vacuum birefringence, where polarized light behaves differently because of the field's influence. That sentence would sound fictional in another era, but it belongs to modern physics. So magnetars are not merely loud neutron stars. They are laboratories where magnetic fields push reality into unusual operating modes. There is also something elegant in how many extremes combine here. Great density, great gravity, rapid rotation, at least often in youth, enormous magnetic stress, explosive releases, compact size. A magnetar is a lesson that scale alone does not measure intensity. 20 kilometers across is tiny by stellar standards, yet within that small sphere lies enough structure and force to send signals across the galaxy. We have seen this theme before. White dwarfs, small compared with stars. Neutron stars, smaller still. Magnetars, same compact scale, but intensified in a different dimension. The universe often packs drama into compact formats. Now, do magnetars last forever? No. Their strongest magnetic phases appear transient on cosmic timescales. Fields decay, rotation slows, activity changes. Some may evolve toward quieter neutron star states over time. Even cosmic ferocity ages. That is strangely comforting. The most intense known magnets do not remain furious indefinitely. They cool, settle, transform, energy disperses. There is a philosophical calm in that. Extremes are often temporary, whether in stars, weather, oceans, or moods. Now let us place magnetars back into our broader question. What is the densest thing in the universe? Magnetars themselves are not denser than other neutron stars simply because their magnetic fields are stronger. Their importance lies in showing that density is not the only axis of extremity. An object can be incredibly dense and also incredibly magnetic. Nature stacks records. The densest known stable matter can coexist with the strongest known magnetic fields. This complicates our instinct to ask for a single, most extreme thing. Reality prefers categories: most dense, most magnetic, most massive, most luminous, most rapidly spinning, most energetic burst, and occasionally one object competes in several divisions at once. Magnetars are overachievers in that sense. There is also a practical narrative shift happening now in our journey. We have examined white dwarfs, neutron stars, pulsars, magnetars. Each stage reveals matter resisting collapse in deeper ways. But what if you were not studying one from safe distance? What if you approached a neutron star directly? What would happen to a human body, to atoms, to time, to shape itself, near something so compact and severe? There are many places in the universe one might dream of visiting. A ringed planet seen from a nearby moon, a quiet valley on Mars at sunrise, the clouds of Jupiter from a very safe floating observatory with excellent insurance, a comet drifting through deep space, perhaps the edge of a nebula where stars are born and nobody expects quick replies. Then there are places better admired from a respectful distance. A neutron star belongs firmly in that category. It is natural to ask what would happen if you fell onto one. Human curiosity has a habit of wandering directly toward danger, provided the danger is theoretical and comfortably far away. So tonight, let us follow the thought experiment carefully, not because it is advisable, because it is illuminating. To begin, imagine approaching a neutron star in a spacecraft. Already, many practical issues would arise before falling onto it becomes relevant. Radiation, intense gravity, possible magnetic fields, orbital mechanics, and the simple challenge of stopping near an object with enormous escape velocity would occupy engineers for some time. But let us be generous and assume you have a capable vessel, a calm pilot, and paperwork that was somehow approved. From a distance, a neutron star may not look especially large. That is one of its first tricks. It contains more mass than the Sun, yet may be only around 20 kilometers across. Cosmic objects train us to associate importance with size. Neutron stars reject this tradition. It might appear as a compact bright point, perhaps surrounded by emissions depending on type. If it is a pulsar, beams sweep space rhythmically. If it is a magnetar, several additional concerns become immediate. As you draw nearer, gravity becomes the central fact of existence. Gravity depends on mass and distance. Since the neutron star's mass is packed into such a tiny radius, the gravitational pull near its surface is immense, much stronger than Earth's, much stronger than that phrase emotionally communicates. On Earth, if you drop a ball, it falls at about 9.8 meters per second squared. Near a neutron star, surface gravity can be around 100 billion times stronger than Earth's, depending on the star's mass and radius. That number is difficult to feel, so let us translate. On Earth, you feel your weight as a manageable downward pull supported by the floor. Near a neutron star, your relationship with down becomes far more personal. Standing on the surface in any ordinary sense would be impossible for a human body. Long before touchdown, forces would become destructive. But before direct crushing, another effect appears: tidal forces. Tidal forces happen because gravity changes with distance. The side of your body closer to the neutron star feels a stronger pull than the far side. We experience mild versions of this from the moon raising ocean tides on Earth. Near a neutron star, mild has left the building. If you fall feet first, your feet are closer to the star than your head. They are pulled harder. This differential force stretches you lengthwise and compresses you sideways. The popular term is spaghettification. It sounds playful, it is not. Near black holes, this effect is famous. Near neutron stars, because the object is compact and gravity gradients are steep, tidal forces can become severe very close to the surface. Depending on approach conditions and the neutron star's exact properties, you may be torn apart before contact. This is one of several reasons tourism remains underdeveloped. Now let us imagine, for learning purposes, that tidal destruction was somehow delayed, and you continued descending intact longer than biology permits. Your speed would increase enormously. Falling onto a neutron star means converting gravitational potential energy into kinetic energy on an extraordinary scale. By the time you reach the surface, impact velocities could become a significant fraction of the speed of light unless some braking mechanism intervened. That means landing is not the correct verb. Releasing vast energy during terminal interaction is closer. Even a grain of dust striking a neutron star at such speed can release notable energy. Matter falling onto neutron stars in binary systems can produce intense X-rays precisely because accreting material crashes into the surface and heats dramatically. So a human body would not arrive as a recognizable traveler. It would arrive as energetic incoming matter. Now let us consider the surface itself. When people hear surface, they imagine soil, rock, metal, ice, or at least something one might point at and say, there it is. A neutron star's outer layer is stranger. Its crust is thought to be composed of nuclei packed in dense lattice structures with free electrons, transitioning deeper into exotic neutron-rich matter. It may be incredibly rigid in some senses, perhaps among the strongest known materials by breaking stress. Yet it is not pavement. It is matter under conditions beyond ordinary chemistry. If something struck it, the interaction would be dominated by high-energy physics, extreme gravity, and intense compression. Now add rotation. Many neutron stars spin rapidly. If the star rotates several times per second, the surface near the equator is moving quickly. Millisecond pulses spin hundreds of times per second. Trying to fall onto a rapidly rotating compact object adds another layer of complication, involving relative velocities, magnetic fields, and frame-dependent regrets. Then there is magnetism. If the neutron star is a magnetar or even a strongly magnetized pulsar, magnetic fields can influence charged particles and surrounding plasma intensely. Electronics would fail long before arrival. Molecular structures might be disrupted under extreme cases. Radiation environments could be severe, so even before gravity physically tears you apart, the environment may become lethally hostile. This raises a useful insight. In ordinary life, danger is often one thing at a time. Too hot, too cold, too high, too fast, too much pressure. Near neutron stars, danger multitasks. Gravity, radiation, speed, tides, magnetic effect, impact energy. Nature has assembled a full committee. Now let us step back and ask a gentler version of the question. What happens to matter that falls onto a neutron star naturally? This is common in binary systems where a neutron star pulls gas from a companion star. That gas spirals inward, forming an accretion disk. Friction and compression heat the disk intensely, causing X-ray emission. When material reaches the surface, it piles up under immense gravity. Hydrogen and helium layers may undergo thermonuclear flashes known as X-ray bursts, so the star can periodically ignite fresh incoming material in explosive surface events. A dead star continues hosting fireworks fueled by stolen gas. Astronomy often rewards patience with sentences like that. What if you dropped something small, say, a pebble? Again, at realistic infall speeds, the pebble would release tremendous energy on impact. Its identity as pebble would end early in the process through heating, ionization, and fragmentation. Objects do not arrive at neutron stars politely labelled. They become plasma, radiation, and incorporated matter. Now, could you orbit safely instead? Safer than landing, certainly. Many objects orbit neutron stars. Companion stars do. Planets have even been found around pulsars. Spacecraft, in principle, could orbit at suitable distances if engineered against radiation and gravity demands. So the lesson is not that neutron stars destroy everything nearby. The lesson is that proximity matters. Far enough away, orbital motion is possible. Too close, conditions escalate rapidly. This is true of many things, including bonfires and office politics. There is also a relativistic twist. Time runs more slowly deeper in strong gravity relative to distant observers. If you hovered near a neutron star and somehow survived, your clock would tick more slowly compared with clocks far away. Not enough for cinematic time travel fantasies in practical scenarios, but measurable and real. So falling toward a neutron star changes not only force and motion, but the rate at which time passes relative to elsewhere. The universe likes layering effects. Now let us imagine the emotional side of this thought experiment. You approach an object smaller than a city yet heavier than stars. It may appear calm from afar. No roaring atmosphere, no giant flames necessarily visible, just compact presence. Then every law of motion becomes severe. This contrast matters because many dangerous cosmic objects do not look dramatic. Vacuum itself has no warning signs. Radiation is invisible. Gravity can be silent. The neutron star teaches humility through understatement. Small silhouette, large consequences. It also teaches something about density. When we say neutron stars are dense, we often focus on teaspoon analogies. But density is not just weight in a small volume, it transforms behaviour. Dense enough mass creates steep gravity. Steep gravity creates tidal forces. Accretion releases huge energy. Matter on the surface exists in exotic forms. Time dilates measurably. Density becomes destiny. That phrase sounds dramatic, but here it is almost bookkeeping. Now, if you somehow stood on a neutron star with magical protection from gravity, heat, tides, and radiation, the horizon would be close because the star is so small. Curvature of light would distort views. A dropped object would accelerate violently. One step might be inadvisable in ways hard to overstate. Fortunately, magic is not part of current mission planning. So what happens if you fall onto a neutron star? Realistically, you are destroyed well before meaningful contact by combinations of tidal forces, radiation, acceleration, and impact energy. Conceptually, you become one more example of how compact mass changes the rules. Scientifically, you reveal that neutron stars are not merely dense curiosities, but environments where gravity dominates ordinary intuition. And narratively, you remind us that some questions are best answered from a comfortable chair. Tonight we have approached one of the universe's harshest destinations and wisely remained hypothetical. A neutron star already sounds like the final answer. Take a massive star, let it die violently, crush its core until atoms fail, electrons merge with protons, and matter becomes a sphere of neutrons packed into city-sized dimensions, with more mass than the sun. Add extreme gravity, rapid spin, powerful magnetic fields, and densities that make mountains in a teaspoon comparisons feel almost routine. Surely that is the end of the road. And yet physics has a habit of asking one more question. What if neutrons are not the final stable arrangement either? What if, under pressures even deeper than those inside known neutron stars, neutrons themselves begin to lose their identity? This possibility leads us to one of the most intriguing hypothetical objects in astrophysics: quark stars. The phrase sounds futuristic enough to belong on the side of a spacecraft, but it emerges from real particle physics and real uncertainty about what matter does when compressed beyond conditions we can reproduce directly. To understand the idea, we should begin with what a neutron actually is. Neutrons are not fundamental particles. They are composite particles made of smaller constituents called quarks. Specifically, a neutron contains one up quark and two down quarks, bound together by the strong force carried by gluons. Protons are similar, containing two up quarks and one down quark. These combinations are called hadrons, particles made of quarks bound into compact packages. In ordinary life, quarks are confined. You do not encounter loose quarks rolling under the sofa or hiding in cereal. They are bound inside protons, neutrons, and related particles. Nature appears to strongly prefer this arrangement under familiar conditions. But familiar conditions do not include the cause of collapsed stars. Inside neutron stars, matter may be compressed to several times nuclear density. The exact behaviour there remains one of modern physics' great open questions. At such densities, neutrons are packed so closely that the boundaries between individual particles may begin to blur, and once you begin blurring neutrons, you are really asking whether their quarks can move more freely. This state is often called quark matter. Instead of matter made primarily of separate neutrons pressed together, the interior could become a dense soup or fluid of deconfined quarks, where quarks are no longer locked neatly inside individual neutrons. If enough of a star consisted of such matter, the object might be called a quark star. So a quark star is not a star made of quarks, in the same sense a wooden table is made of wood. It is a compact stellar remnant whose matter may exist in a phase where quark degrees of freedom dominate. That is less catchy, but more accurate. Now let us ask why scientists take this seriously. Because the strong force behaves differently depending on distance and energy scale. At very short distances, quarks can interact in ways that make deconfinement plausible under sufficiently extreme pressure or temperature. In particle colliders, brief quark-gluon plasma states have been created at immense temperatures. These are not stars, but they show that quark matter is not fantasy. Nature allows such phases under certain conditions. The question is whether cold, ultra-dense stellar interiors also host them. This is much harder to answer. We cannot drill into neutron stars. We cannot scoop core samples. We infer internal states through mass measurements, radii, spin behavior, cooling, merger signals, and theoretical models called equations of state, which describe how pressure relates to density. Different internal compositions predict different relationships between mass and size. So when astronomers measure an especially heavy neutron star, or a surprisingly small radius, or unusual cooling behavior, theorists immediately become interested. Could quark matter be involved? Sometimes yes, sometimes no. Often, more data needed. The official slogan of honest science. Now, if quark stars exist, how would they compare with neutron stars? Likely they would be similar in broad appearance, compact, extremely dense, small radius, strong gravity, perhaps pulsating or rotating, perhaps with crusts or surface layers depending on exact models. From a distance you would not look through a telescope and see a label reading quark star, now with improved particle content. Distinguishing them observationally is difficult. That is why none are confirmed with consensus as of now. There are candidate objects whose properties have inspired speculation. Some compact stars may appear smaller or denser than standard neutron star models comfortably predict. Certain unusual bursts or cooling rates have been discussed in this context, but evidence remains inconclusive. This is frontier territory. Now let us go one step deeper, because astrophysics rarely stops where comfort begins. Some theorists propose a particularly stable form called strange quark matter. This would include not just up and down quarks, but strange quarks as well. Under certain models, matter containing up, down, and strange quarks might be energetically favourable at extreme density. If true, stars composed largely of this phase are often called strange stars. Yes, that is the actual term. Science can be wonderfully direct when naming gets tired. The idea is subtle but dramatic. Perhaps the true ground state of very dense matter, is not neutron matter at all, but strange quark matter. If so, some neutron stars might actually be strange stars in disguise. Again, this remains hypothetical, but it is the sort of hypothesis that keeps physicists awake, which is useful because someone should be. Would quark stars be denser than neutron stars? Potentially yes, depending on the model. If quark matter packs differently, or allows greater compactness before black hole collapse, some quark stars might occupy smaller radii for the same mass. That possibility matters for our larger theme. We're searching for the densest forms of stable matter nature may permit. White dwarfs gave us electron-supported matter. Neutron stars gave us matter beyond atoms. Quark stars, if real, would push beyond neutrons. Each step removes another familiar layer of structure. Molecules gone, atoms gone, nuclei no longer sufficient, neutrons themselves perhaps no longer final units. This layered stripping of identity is one of the most striking narratives in extreme astrophysics. Matter keeps becoming simpler and stranger at the same time. Now, what would it be like on a quark star? Likely unpleasant. Surface gravity would be immense. Radiation environments could be severe. If a crust exists, it would differ from ordinary matter in exotic ways. If bare quark matter were exposed, the surface physics could be astonishingly unfamiliar. Fortunately, direct tourism remains improbable. There is another interesting consequence of quark matter: cooling. Compact stars lose heat through neutrino emission and later photon radiation. Different interior particle processes can alter cooling rates. If quark matter exists, it may leave signatures in how rapidly a star cools over time. So astronomers watch temperatures. Again, dead stars become data sources. Rotation and glitches may also reveal clues. The internal viscosity, superfluid behavior, and cross-core coupling of quark-containing stars could differ from ordinary neutron star expectations. Thus, when a pulsar twitches slightly or cools oddly, someone somewhere wonders whether quarks are involved. This is the glamorous life of modern astrophysics. Now let us be careful with language. A quark star is not a settled category like Earth or Jupiter. It is a theoretically motivated possible class of compact object not yet observationally confirmed beyond serious doubt. That distinction matters. Science progresses through proposals, tests, revisions, and patience. Sometimes ideas survive, sometimes they do not. Sometimes they wait decades for better instruments. Quark stars may be real and hiding among neutron stars, or neutron star matter may already explain current observations without needing a separate class. Or reality may contain mixed phases more complicated than either neat label suggests. The universe often chooses option 3. There is something beautiful in this uncertainty. It reminds us that even after discovering black holes, galaxies, exoplanets, gravitational waves and cosmic background radiation, we still do not fully know what matter does when squeezed hard enough. The cosmos has not finished surprising us, and perhaps surprise is built into scale. The deeper we go into the small, or the denser we go into the compact, the more categories soften. Solid becomes lattice. Lattice becomes degenerate matter. Degenerate matter becomes nuclear fluid. Nuclear fluid may become quark matter. Language follows behind, carrying luggage. Now place quark stars beside our broader question. What is the densest thing in the universe? If we mean confirmed stable objects, neutron stars remain the strongest evidence-backed answer. If quark stars exist, they may represent an even denser stable state. If strange stars exist, the hierarchy becomes more interesting still. And beyond all of these lies, black holes, where density becomes conceptually thornier because of horizons and uncertain singularities. So quark stars occupy a fascinating middle ground, not yet confirmed, not absurd, deeply plausible enough to study seriously, exotic enough to capture imagination. There is also a human lesson here. When we think we have reached the bottom layer, we often discover another beneath it. Atoms once seemed final, then nuclei, then protons and neutrons, then quarks. Now perhaps matter under pressure reorganizes again in ways still unresolved. Knowledge tends to become more subtle, not less. There is a recurring habit in science. Whenever we become comfortable saying, "Surely this is the final layer," reality quietly asks, "Would you like to go one step deeper?" Atoms once seemed fundamental, then came nuclei, then protons and neutrons, then quarks. Stars once seemed simple glowing spheres, then they became furnaces, then remnants, then white dwarfs, neutron stars, pulsars, magnetars, possible quark stars. Every time certainty settles into a chair, the universe removes the chair. Tonight we arrive at one of the boldest ideas in dense matter physics, strange matter. The name sounds as if scientists temporarily gave up and simply described their mood. In truth, it refers to a specific theoretical possibility involving strange quarks, one of the known varieties, or flavours, of quark. To understand why this matters, let us begin with ordinary matter. Most of the visible matter around us is built from atoms. Atoms contain nuclei made of protons and neutrons. Protons and neutrons themselves are made of up and down quarks bound together by the strong force. So the chair, the clouds, the moon, your bones, your tea mug, and many regrettable household drawers are all, at deeper levels, arrangements of up and down quarks. These are the everyday quarks of ordinary baryonic life. Strange quarks also exist in nature, but under normal conditions they do not build stable everyday matter around us. They are heavier than up and down quarks and typically appear in short-lived particles created in energetic environments, then decay. Nothing in your kitchen is made of stable, strange quark furniture. This is probably for the best, but under extreme pressure where energies and densities rise enormously, the rules may change. Inside neutron stars, or objects even more compact, the distinction between particle types can shift. If matter is compressed enough, it may become energetically favourable for some down quarks to transform into strange quarks. Why would that help? Because adding a third quark flavour can, under some models, allow the system to distribute particles among available quantum states more efficiently, lowering total energy. This is subtle and powerful. Nature often prefers lower energy arrangements. If a strange quark mixture lowers the energy of ultra-dense matter, then matter containing up, down and strange quarks might become more stable than neutron matter under certain conditions. That hypothetical state is often called strange matter, or more specifically, strange quark matter. And if large chunks of it could exist stably, some compact stars might be strange stars. Now pause for a moment. This means there is a serious theoretical proposal that the densest stable form of matter might not be neutrons packed together, but a sea of up, down and strange quarks in a more favourable arrangement. That is a dramatic claim. It is also unconfirmed, which makes it scientifically exciting and emotionally tidy. Let us unpack why anyone believes this is worth considering. In the 1980s, physicists such as Edward Witten and others explored the possibility that strange quark matter might be the true ground state of strongly interacting matter at zero pressure, meaning, in principle, more stable than ordinary nuclear matter. If correct, the implications would be enormous. Neutron stars might actually convert into strange stars. Tiny fragments called strangeles might exist. The matter composing everyday atoms would remain metastable in practice, because transitions could be extraordinarily suppressed or require special conditions. Reality would contain a deeper, preferred state, hidden behind large barriers. That sounds like science fiction, but it is legitimate theoretical work. Now, before anyone worries that the table may suddenly transform into exotic quark goo, current evidence offers no reason for such domestic concern. Ordinary matter appears spectacularly durable on human timescales. If strange matter is more stable under some conditions, transitions from everyday matter are not casually happening in living rooms. Your furniture remains committed to conventional existence. Still, in the hearts of collapsed stars where densities soar, the question becomes meaningful. Could neutron star cores convert partially or entirely into strange matter? Could some observed compact stars be strange stars already? Could strange matter be denser than neutron matter while remaining stable? These remain active topics of study. Now let us compare strange matter with neutron star matter conceptually. Neutron star matter is often described as matter beyond atoms, dominated by neutrons under immense pressure, with possible admixtures of protons, electrons, muons, hyperons, or more exotic phases depending on depth. Strange matter goes further. Instead of neutrons remaining the main identity, quarks themselves become the relevant degrees of freedom, including strange quarks. Matter is no longer best thought of as packed neutrons, but as a dense quark fluid or phase. This may permit different pressure density relationships, different radii for given masses, different cooling behavior and different surface properties. In simpler terms, same cosmic weight class, different internal recipe. Now, would strange matter be denser? Possibly. Depending on the equation of state, strange stars could be more compact than typical neutron stars of similar mass. Smaller radius with similar mass means greater average density. That matters greatly for our larger question of the densest thing in the universe. If strange stars exist and are more compact while remaining stable, they may outrank ordinary neutron stars as the densest stable stars short of black holes. But nature has not yet signed the paperwork. Observationally, distinguishing neutron stars from strange stars is difficult. Both would be compact, heavy, and small. Both might pulse. Both could accrete matter. Both could produce X-rays. From far away they can wear similar clothes, so scientists look for clues, mass radius measurements, cooling rates, surface emissions, spin behavior, merger signatures, moment of inertia estimates, tidal deformability in gravitational wave events. Each observation acts like a question asked politely across light years. What are you made of in there? So far, the answers remain suggestive rather than final. Some observed compact stars seem massive enough to challenge softer equations of state. Others appear small enough to spark speculation. Gravitational wave detections from neutron star mergers have begun constraining possibilities further. The story is developing in real time. Now let us discuss strangeless briefly, because once one enters this subject, vocabulary becomes adventurous. A strangelay would be a small lump of strange matter, perhaps ranging from microscopic to larger scales depending on theory. If stable, such objects might in principle travel through space, emerge from collisions, or exist in rare environments. Have we found one conclusively? No. Many searches have been conducted in cosmic rays and collider contexts, but no accepted detection has settled the matter. Still, the concept shows how deeply physicists are willing to follow implications. If strange matter is possible, what sizes can it take? Science asks all available questions. There is also a profound lesson hiding here. The familiar world is not necessarily the only stable arrangement matter can take. It may simply be the arrangement favoured under everyday pressure and temperature. Under crushing gravity, matter may choose differently. This theme repeats across nature. Carbon becomes diamond, hydrogen becomes metallic, electrons become degenerate support, neutrons dominate stellar remnants, quarks may deconfine, strange quarks may join the party, pressure changes preference. That phrase could summarise much of planetary and stellar physics. Now, why are strange quarks called strange quarks? Because particle physics naming emerged historically through a mix of mathematics, discovery order, and human whimsy. Strangeness originally described certain behaviours of particles produced in high-energy interactions. So yes, one of the candidate ingredients of ultra-dense stars is literally called strange. The universe occasionally helps with branding. Would a strange star look different to the eye? Probably not in any easy cinematic sense. It would not glow green and hum ominously. Its visible appearance would depend on temperature, surroundings, accretion, magnetic field, and emission mechanisms. The real differences are internal and measurable only through careful astrophysical inference. This is often how science works. The dramatic truths are not always visual. Now let us return to the hierarchy of density. Ordinary matter, atoms with room inside, white dwarfs, matter supported by electrons, atoms heavily crushed, neutron stars, matter beyond atoms dominated by neutrons, quark stars, hypothetical deconfined quark matter, strange stars, hypothetical quark stars including strange quarks in stable form, black holes, objects where collapse crosses the event horizon, and density becomes conceptually more complicated. Each step removes familiar structure and increases compression. Each step asks whether a deeper level becomes relevant. This is one reason the question, "What is the densest thing?" is richer than it first sounds. It is not merely a ranking contest. It is a guided tour through how matter reorganizes under pressure. There is also something calming in uncertainty. We do not yet know every answer. That means the night sky still contains unsolved interiors. Objects we can detect precisely may hide phases of matter no laboratory can reproduce fully. Human knowledge has reached pulsars, mergers, relativistic timing, X-ray telescopes, and gravitational wave observatories. And still, the core of a compact star may keep its secret a little longer. That is not failure. That is frontier. For a long time in our journey, gravity has been opposed. Stars resist it with heat from fusion. White dwarfs resist it with electron degeneracy pressure. Neutron stars resist it with neutron degeneracy pressure and nuclear forces. Perhaps even stranger states of matter may offer temporary support in deeper regimes. At every stage, gravity presses inward and something pushes back. That struggle creates structure. Planets, stars, stellar remnants, atmospheres, mountains and galaxies all depend in some way on balances between collapse and resistance. But there are circumstances in which resistance fails. Not gradually, not politely, completely. And when that happens, one of the most extraordinary objects in physics can form, a black hole. Few scientific ideas have entered public imagination so thoroughly. Black holes appear in films, jokes, headlines, metaphors, and the occasional office meeting description. They are often treated as cosmic vacuum cleaners that eat everything nearby while making ominous noises. The reality is stranger, calmer, and more precise. A black hole is a region of space-time where gravity has become so strong that once you cross a certain boundary, escape outward is no longer possible. Not even for light. That boundary is called the event horizon. We will explore it more deeply later. For now, think of it as the point beyond which return is cut off. Outside the horizon, gravity behaves according to the mass, spin, and charge of the black hole. Objects can orbit. Light can bend. Matter can fall in. But once the horizon is crossed, paths leading back outward no longer exist in the usual sense. This is what it means for gravity to win completely. No known pressure remains to halt collapse before the horizon forms. To understand how black holes are born, let us return to massive stars. A very massive star spends its life fusing elements in stages. When support fails, the core collapses. Sometimes neutron degeneracy pressure halts collapse, leaving a neutron star. But if the core mass is high enough, even neutron support cannot hold. Gravity continues compressing matter inward. The radius shrinks below a critical size associated with the mass. Once enough mass is confined within that radius, an event horizon forms. A stellar mass black hole is born. For a non-rotating black hole, the characteristic radius is called the Schwarzschild radius. It scales directly with mass. For the Sun's mass, this radius would be about 3 kilometers. That means if the Sun were somehow compressed into a sphere roughly 3 kilometers in radius, without changing its mass, it would become a black hole. This is a useful fact because it shows black holes are not defined by infinite size or cosmic greed. They are defined by compactness, enough mass, small enough region, gravity changes category. Now, black holes also form in other ways. Supermassive black holes inhabit the centres of most large galaxies, including our own Milky Way. These monsters contain millions or billions of solar masses. How exactly they grew so large so early in cosmic history remains an active area of research involving accretion, mergers, and perhaps early massive seed objects. There may also be intermediate mass black holes between stellar and supermassive scales, and perhaps primordial black holes formed in the early universe, though the latter remain hypothetical. So black holes are not one object type so much as a family defined by the same core principle. Gravity crossed the line. Now let us address a common misunderstanding. Black holes do not suck everything nearby like vacuum cleaners. If the Sun were magically replaced by a black hole of the same mass, Earth's orbit would remain essentially the same. We would have many new concerns about warmth and agriculture, but orbital mechanics would continue. Why? Because gravity at a distance depends on mass and separation. Replace one object with another of equal mass, and faraway orbits need not change dramatically. The special nature of a black hole appears when you get close enough. Near the horizon, space-time curvature becomes extreme. Stable orbits may vanish inside certain radii. Light paths bend sharply. Tidal forces can become severe, especially for smaller black holes. Distance matters. As with bonfires and awkward conversations, proximity changes everything. Now let us ask the question tied to tonight's larger theme. Are black holes the densest things in the universe? The answer is yes, no, and define your terms. If one follows classical general relativity inward, collapse leads to a singularity, a point where density becomes infinite and our equations break down. Infinite density would seem to win any contest immediately, but many physicists suspect that singularities signal incomplete theory rather than literal physical points existing neatly in nature. We do not yet have a finished quantum theory of gravity to describe what truly happens at those scales, so black holes are certainly the most compact confirmed objects of large mass, but whether they contain actual infinities remains unresolved. This makes black holes scientifically richer than simple slogans allow. They are not merely holes, they are places where our best theories meet their limits. Now consider what a black hole looks like. By itself, a black hole emits no light from inside the horizon. The horizon appears dark because light cannot escape, but black holes are often visible indirectly through surroundings. Matter falling toward a black hole may form an accretion disk. Gas in the disk heats through friction and compression, glowing intensely in X-rays or visible light depending on scale and conditions. Jets may be launched from regions near rotating black holes through magnetic processes tied to the disk and spin. So many of the brightest objects in the universe involve black holes not because the hole itself glows, but because nearby matter suffers spectacularly. This distinction matters. The darkness creates brilliance around it. There is poetry in that, though we promised not to overdo poetry. Now let us discuss size. A stellar mass black hole might be tens of kilometers across at the horizon. A supermassive black hole can have a horizon larger than planetary orbits. Yet oddly, larger black holes can have gentler tidal forces at the horizon than small ones, because the gradient of gravity there depends on size. That means crossing the horizon of a supermassive black hole, in principle, might feel less violently dramatic at that moment than crossing near a small stellar black hole. The later consequences remain poor, but first impressions vary. Again, the universe enjoys nuance. Black holes also spin. Most realistic black holes likely rotate because their progenitor matter had angular momentum. Rotating black holes are described by the Kerr solution in relativity. Spin changes the surrounding geometry, creates an ergosphere where space-time is dragged around, and allows additional energetic phenomena. Even emptiness can rotate impressively when shaped by gravity. There is another remarkable feature. Black holes are simple from the outside. According to classical no-hair ideas, an isolated black hole is characterized mainly by mass, spin and charge. Charge in astrophysical settings is usually expected to be negligible because surrounding plasma neutralizes it. So from far away, black holes may seem less detailed than stars. Complex matter collapses, but the external description becomes minimal. Many histories, few final labels. This simplicity hides deep puzzles, such as the information paradox. What happens to the information describing matter that falls in, especially when black holes slowly evaporate through Hawking radiation over immense timescales? That question remains one of modern theoretical physics' great battlegrounds. So black holes are not merely dense endpoints, they are engines of unanswered questions. Now imagine approaching one. Far away you might orbit normally if conditions permit. Closer in, gravitational lensing distorts views. Light from behind bends around the hole. Time dilation grows stronger relative to distant observers. Tidal forces increase. The horizon approaches as a geometric boundary, not a solid surface. There is no wall to hit at the horizon itself in the simplest idealized cases. It is a point of no return defined by causal structure. This is difficult for intuition because we are used to boundaries being things. Fence, door, shoreline. Black hole boundaries are rules, and rules can be harder to picture than walls. There is something philosophically powerful in black holes representing not merely extreme matter, but extreme geometry. Neutron stars ask what matter does under pressure. Black holes ask what space-time does when matter compresses enough. That is a shift in the story. Matter stops being the main character. Geometry takes over. Tonight we have reached the stage where gravity no longer negotiates. It does not need thermal pressure, electron pressure, or neutron pressure to be overcome one by one. Those chapters are finished. The horizon forms. Escape closes. Yet many mysteries remain just outside and inside that boundary. What exactly is an event horizon like? What happens to time there? What does inside even mean when paths outward are impossible? And if singularities are not the final truth, what replaces them? Boundaries are usually easy to understand. A shoreline separates land from sea. A doorway separates one room from another. A fence separates your garden from the neighbour's ambitious opinions about landscaping. A cliff edge separates stable decisions from unstable ones. We are comfortable with borders because they are visible, tangible, and often accompanied by signs. The event horizon of a black hole is none of these things. It has no painted line, no glowing ring in empty space, no surface made of metal, stone, gas, or ice. You cannot tap it with a stick and hear a sound. It is not a wall. And yet it is one of the most important boundaries in physics. The event horizon is the edge where return becomes impossible. More precisely, it is the boundary around a black hole beyond which no signal travelling at or below the speed of light can escape to the outside universe. That includes light itself, hence the name black hole. To understand why this happens, let us begin with escape velocity. If you throw a ball upward on Earth, gravity slows it. Throw harder, it rises higher. Throw fast enough, about 11.2 kilometers per second, neglecting atmosphere, and it can escape Earth entirely. Escape velocity is the speed needed to leave a gravitational field without further propulsion. For larger masses or smaller radii, escape velocity increases. Now imagine compressing more and more mass into a smaller and smaller space. At some point, the escape velocity at the surface reaches the speed of light. Beyond that compactness, even light cannot get out. This does not mean light is too heavy or got lazy. It means space-time geometry around the mass is such that outward paths no longer lead to distant escape. That critical boundary is the event horizon. Already we notice something subtle. The horizon is not defined by material surface conditions. It is defined by geometry and causality. It marks which future paths remain possible. Outside the horizon, you can still move away, send signals outward, orbit, or choose trajectories that avoid falling in. Inside the horizon, every future-directed path leads deeper inward, not because something grabs you with claws, because the structure of space-time leaves no route back out. This is why a return becomes impossible. Now let us confront one of the strangest aspects of the event horizon. If you are falling freely into a sufficiently large black hole, you might not notice any dramatic local event exactly at the horizon itself. No alarm necessarily sounds. No cosmic customs officer stamps your passport. No invisible glass shatters. In classical general relativity, the horizon is not a physical membrane in the ordinary sense. It is a global boundary defined by the causal structure of space-time. That makes it difficult for human intuition. We expect edges to feel like edges. The event horizon may feel locally ordinary while being globally decisive. It is like crossing a line on a map where roads back no longer exist, yet the pavement beneath you looks unchanged. Now, to a distant observer watching you fall, things appear differently. As you approach the horizon, your clock seems to run slower relative to theirs because of gravitational time dilation. Light you emit becomes increasingly redshifted and delayed. You appear to slow, fade, and asymptotically approach the horizon. From far away, it may seem you never quite cross. From your own perspective, assuming ideal conditions, you cross in finite proper time. Both descriptions arise from relativity and differing coordinate viewpoints. This often sounds paradoxical, until one remembers that time and simultaneity are not absolute in Einstein's universe. Two observers can describe timing differently without contradiction. Reality permits more nuance than everyday clocks suggest. Now let us ask what the horizon size actually is. For a non-rotating black hole, the Schwarzschild radius is r sub s equals 2 gm over c squared. This means the horizon radius grows directly with mass. A black hole with the Sun's mass would have a horizon radius of roughly 3 kilometers. A black hole 10 times the Sun's mass would be about 30 kilometers in radius. A supermassive black hole millions of times the Sun's mass could have a horizon spanning millions of kilometers. Same concept. Very different scale. This matters because tidal forces at the horizon depend strongly on size. For a small stellar mass black hole, tides near the horizon can be severe. For a supermassive black hole, they may be relatively gentle at the moment of crossing. So paradoxically, bigger black holes can be more polite initially. The later journey remains inadvisable. Now, black holes in nature likely rotate. Rotation changes the story. A spinning black hole has an event horizon too, but also an ergosphere outside it, where space-time itself is dragged around by rotation so strongly that remaining stationary relative to distant stars becomes impossible. This effect is called frame dragging. Even space around the hole is not merely sitting there, it is participating. The event horizon remains the true no-return boundary, but spinning geometry adds layers of complexity and opportunity, including ways to extract rotational energy indirectly through physical processes. The universe rarely settles for the simplest version. Now let us talk about why horizons matter scientifically. They are central to black hole thermodynamics. In the 1970s, physicists including Bekenstein and Hawking showed that black holes can be assigned entropy proportional to horizon area, and that quantum effects imply black holes emit Hawking radiation. This was revolutionary. A boundary once thought purely absorptive acquired temperature, entropy, and eventual evaporation timescales. The event horizon became not just geometry, but thermodynamic bookkeeping. This deepened a major puzzle, the information paradox. If matter-carrying information falls into a black hole, and the black hole later evaporates thermally, what happens to the information? Destroyed? Encoded somehow? Returned subtly in radiation? Modern theory strongly leans against fundamental information destruction, but the precise mechanism remains a profound topic. So the horizon is not merely an edge in space. It is where gravity, quantum theory, thermodynamics, and information theory all begin arguing. Few places in physics host such accomplished disagreement. Now let us imagine standing near a black hole, again conceptually, with excellent protective assumptions. You look outward and see distorted stars due to gravitational lensing. Light from behind bends around the hole, creating arcs and rings. Time outside appears sped up relative to you if you hover deep enough. Your engines complain. Your accountant resigns. The horizon itself may not glow unless surrounding matter is present. Many famous images of black holes show the bright accretion flow around a central dark shadow. The dark region relates to photon capture and lensing geometry, not a literal hole cut into space. The boundary itself remains invisible except through its effects. This is another recurring lesson. Some of the most important things in nature are known indirectly. Magnetic fields by what they move, atoms by how they scatter, dark matter by gravity, horizons by missing escape routes. Now there is a philosophical calm in the idea of an event horizon. It is a place where possibility narrows to one direction. Outside, futures branch widely. Inside, all future paths point inward. This sounds dramatic because it is, but it also echoes simpler truths. Many systems have thresholds after which reversal becomes difficult or impossible. Avalanches, critical reactions, financial decisions involving inflatable furniture. The horizon is the pure geometric version of that idea. Crossing changes available futures. Now, one common misunderstanding should be cleared gently. The event horizon is not a suction boundary pulling everything from vast distances. Black holes influence distant objects through gravity according to their mass, just as any massive body would. The horizon matters when you come close enough. Far away, stars can orbit a supermassive black hole for ages quite stably, as stars do around Sagittarius A star. Near the horizon, the special nature of black holes becomes decisive. Distance remains the difference between astronomy and immediate regret. Now let us connect the horizon back to our larger question of density. White dwarfs and neutron stars have surfaces made of matter. They are compact objects with definable material boundaries. Black holes replace that kind of surface with a causal boundary. This is a conceptual leap. The densest stable stars ask how matter resists collapse. The event horizon asks what happens after resistance fails. Matter no longer defines the accessible edge. Space-time does. That is why black holes feel so different from other dense objects. They are not simply more compressed stars. They belong to another category of physical description. Tonight we have reached the threshold where outward messages cease, where geometry outruns ordinary intuition, where boundaries become invisible but absolute. Yet the horizon is only the beginning of the mystery. If nothing escapes from inside, what lies beyond it? Is there truly a singularity? Does quantum gravity replace it with something else? And why do some black holes, despite their reputation for infinite density, become surprisingly low in average density when they grow enormous? If black holes are famous, singularities are legendary. They are often presented as the final destination inside a black hole, a point of zero size, infinite density, and infinite curvature where matter is crushed completely, and the known laws of physics surrender their badges. It is a dramatic image. A star collapses, gravity wins, everything falls inward. At the centre waits a point beyond comprehension. This picture has become so common that many people treat it as settled fact. But science is more careful than legend. The singularity is not something we have directly observed. It is what classical general relativity predicts, when its equations are extended into regimes where quantum effects are expected to matter enormously. That distinction is essential. A singularity is, in one sense, a signpost in mathematics. It often means our description has reached a place where quantities diverge and the model stops being complete. Sometimes infinity in equations reveals reality. Sometimes it reveals missing physics. The question of black hole singularities lives exactly in that tension. To understand why, let us begin with collapse. Imagine a massive star whose core can no longer resist gravity. Electron degeneracy fails. Neutron degeneracy fails. No known pressure stops further contraction before the event horizon forms. Matter continues inward. General relativity describes gravity not as a pulling force in the old Newtonian sense, but as the curvature of space-time caused by mass energy. When enough mass is concentrated, space-time curves intensely. If collapse continues under the classical equations, the matter is driven toward a state where volume tends toward zero, while density tends toward infinity. That limiting object is called a singularity. For a non-rotating idealized black hole, the simplest picture places it at the center as a point. For rotating black holes, the classical solution predicts a ring singularity, adding geometry that sounds suspiciously designed by theorists after a long week. Either way, infinities appear. Infinite density, infinite tidal curvature, infinite breakdown of calm conversation. Now, in mathematics, infinities can be meaningful, but in physics, when infinities emerge in places where measurable reality should be finite, we become cautious. For example, if a calculation predicts the temperature in your kitchen is infinity, you do not immediately buy special oven mitts. You suspect the model has gone wrong, or been applied outside its useful range. Physicists feel similarly about singularities. General relativity is extraordinarily successful. It predicts gravitational lensing, black holes, orbital precession, gravitational waves, time dilation, and much more with stunning accuracy. But it does not include quantum mechanics in a complete way. At everyday scales, this is fine. At atomic scales, quantum theory dominates. At black hole centers, both extreme gravity and extreme smallness matter simultaneously. That is exactly where we expect general relativity alone to be incomplete. So when relativity predicts a singularity, many physicists interpret it less as nature definitely contains literal infinities, and more as our current framework has reached its limit. That is an intellectually humbler and scientifically healthier stance. Now let us ask what infinite density even means. Density is mass divided by volume. If a finite mass is compressed into zero volume, density mathematically diverges toward infinity. But zero volume is itself a problematic physical statement when quantum uncertainty and possible quantum gravitational structure should become relevant. Below certain scales, the classical notion of smooth space-time may no longer apply in the way we're used to. The concept of a geometric point may not survive unchanged, so the singularity could be telling us that treating space-time as continuous all the way down stops working. That would not be shocking. Many classical ideas fail at sufficiently small scales. Now, singularities are not merely optional curiosities in relativity. There are famous singularity theorems developed by people including Roger Penrose and Stephen Hawking, showing that under broad conditions, gravitational collapse leads to geodesic incompleteness, roughly meaning paths through space-time cannot be extended indefinitely in the usual way. This is more precise than there is a little infinitely dense dot. Theorems indicate breakdowns are generic features under certain assumptions, but they do not themselves provide the final microscopic replacement. They show where the map ends. They do not supply the new terrain. That is where quantum gravity enters. Quantum gravity is the unfinished project of unifying general relativity with quantum mechanics into a consistent framework describing space-time under extreme conditions. Candidates include string theory, loop quantum gravity, and other approaches. None yet commands universal confirmation as the final answer. Different models suggest different possibilities for what replaces singularities. Perhaps matter rebounds in some way. Perhaps a finite ultra-dense core forms. Perhaps space-time becomes discrete. Perhaps black holes connect to other regions through speculative structures. Perhaps information is encoded holographically on boundaries. Perhaps reality chooses an option no current seminar slide fully captures. The universe has a history of selecting option 5. Now let us examine why singularities remain useful despite uncertainty. Even if the literal centre is not a true point of infinity, black hole solutions with horizons and strong field behaviour describe observations extremely well outside whatever quantum core exists. Astronomers do not need to know the exact central replacement to study orbits around Sagittarius A star or image the shadow of M87 star. Just as engineers can use fluid equations without tracking every molecule, astrophysicists can use exterior black hole solutions without resolving the deepest centre. So singularity uncertainty does not make black holes doubtful. It makes their interiors incomplete in theory. That is a different issue. Now let us talk intuition. People often imagine all the matter that formed a black hole as sitting at the centre, like crushed debris at the bottom of a cosmic drain. But inside a black hole, ordinary ideas of space and time become tricky. The radial direction inward can behave more like a time direction in some descriptions. Moving inward is less like choosing to walk to the centre, and more like moving toward a future event you cannot avoid. This is one reason simple pictures fail. The singularity is not merely an object in a room. It is a feature of space-time structure. Again, geometry takes over from household metaphor. Now consider rotating black holes. The classical Kerr solution predicts a ring singularity rather than a point. This has inspired many speculative stories about wormholes and alternate universes. Most of these leap well beyond what evidence supports. The safe conclusion is simpler. Rotation changes internal geometry significantly. Whether the classical ring survives quantum corrections is unknown. Science tolerates imagination best when labelled clearly. There is also a profound philosophical angle. Singularities represent places where explanatory language reaches its current boundary. We can describe approach. We can describe external effects. We can derive the need for deeper theory. But we cannot yet state confidently what truly happens at the final centre. That is not weakness. That is honest frontier science. Many major breakthroughs begin where equations become uncomfortable. Now, how does this relate to our central theme of density? If singularities were literal, then black holes would contain infinite density and win any contest automatically. But because literal infinities are suspect physically, the answer becomes subtler. Black holes are certainly the most compact confirmed macroscopic objects. Their horizons define regions of no return. Their interiors likely contain states beyond known physics. But whether infinite density is real or shorthand for theoretical breakdown remains open. This means neutron stars may be the densest confirmed matter we can meaningfully model, while black holes represent the regime where the concept of density itself becomes problematic. That distinction is valuable. Sometimes the densest thing is not a number, but a warning that old categories are failing. Now let us imagine the emotional shape of this idea. Human beings often want endings to be concrete. At the centre there is a point. At the bottom there is a floor. At the smallest scale there is a final brick. But nature repeatedly complicates such hopes. Atoms became quantum clouds. Particles became fields and excitations. Space became dynamic geometry. Black hole centres may become something other than points. The singularity story reminds us that simplicity at the edge of knowledge is often temporary. Tonight we have reached the place where mathematics says infinity, and physics replies, probably not so fast. There is a special kind of sentence in science that sounds final but is actually a placeholder. The singularity is a point of infinite density. It has rhythm. It sounds decisive. It appears to settle the matter with admirable confidence. One can imagine it printed in bold letters beside an artist rendering of a black hole consuming something expensive. And yet many physicists hear that sentence differently. They hear, our current equations stop being trustworthy here. That difference matters. Tonight we arrive at one of the most honest and fascinating questions in modern physics. Do singularities really exist? Or are they signs that our theories are incomplete? To begin gently, let us recall what a singularity means in the black hole context. General relativity describes gravity as the curvature of space-time. Matter and energy tell space-time how to curve. Space-time tells matter how to move. This framework has passed extraordinary tests. It predicts gravitational lensing, time dilation, Mercury's orbital precession, black holes, gravitational waves, and much more. When the equations of general relativity are applied to continued gravitational collapse, they indicate that matter can be driven into a state where curvature becomes unbounded and density tends toward infinity. That predicted endpoint is called a singularity. But physicists become suspicious whenever infinities appear in places meant to describe measurable nature, not because infinity is illegal, because infinity often means a model has been pushed past its proper domain. Suppose a weather model predicted an infinite wind speed over your garden. You would not immediately nail furniture to the floor. You would first suspect the model has omitted something important or broken under conditions it was not built to handle. Likewise, if an electrical equation predicts infinite current in a real device, engineers look for missing resistance, idealizations, or assumptions that fail physically. In science, infinities are frequently warning labels, and black hole singularities may be one of the grandest warning labels we have. Now, why might general relativity fail there? Because relativity is classical. It treats space-time as smooth and continuous. It does not incorporate quantum mechanics in a complete unified way. Quantum mechanics governs very small scales, uncertainty, particle behavior, vacuum fluctuations, and phenomena that classical descriptions cannot capture fully. Near a supposed singularity, two things happen at once. Gravity becomes extreme. Relevant scales become tiny. That is exactly where both relativity and quantum theory should matter simultaneously. And we do not yet possess a fully confirmed theory that unites them. So asking general relativity alone to describe the center of a black hole may be like asking a road map to explain ocean currents, useful nearby, wrong at the deepest point. This is why many physicists suspect singularities do not literally exist as physical points of infinite density. Instead, some new quantum gravitational structure may replace them. Now, let us be careful. This does not mean black holes are fake. Black holes are strongly supported by observation. We see stars orbiting the compact object at the center of Milky Way. We have imaged the shadow region around M87 star and Sagittarius A star. We detect mergers through gravitational waves. We observe accretion disks and relativistic jets. The uncertainty concerns the deepest interior, not the existence of horizons or strong field compact objects. That distinction is crucial. Now let us explore what might replace singularities. There is no consensus final answer, but several broad ideas exist. One possibility is that quantum pressure or quantum geometry halts collapse before infinite density is reached. Matter might compress into an ultra-dense but finite core. Instead of a point of zero size, there could be a tiny region of extreme but finite density. Another possibility comes from loop quantum gravity-inspired models, where space-time itself may have discrete structure at the smallest scales. If space is quantized rather than infinitely divisible, classical infinities may never form in the first place. In some versions, collapse could lead to a bounce or transition. Another family of ideas comes from string theory, where fundamental objects are not point particles but extended strings or branes. Under such frameworks, the interior of black holes may be described very differently from classical singular points. There are also fuzzball proposals, firewalls, gravastars, Planck stars, holographic descriptions, and several other candidates. If this sounds like a lively disagreement, that is because it is. Physics at the edge of knowledge often contains multiple plausible maps and no final road signs yet. Now, one may ask, if we do not know the inside, how can we trust anything? Because science often works in layers of reliability. We know the exterior gravitational behaviour of black holes extremely well in many regimes. We know event horizons are strongly supported indirectly. We know mergers happen. We know matter orbiting compact dark objects behaves as expected. What happens at the deepest centre may remain uncertain without undermining the well-tested outer description. A useful analogy is Earth. For centuries, people understood tides, seasons, and planetary motion without knowing the exact composition of Earth's core. Outer behaviour can be known while inner details remain under investigation. Black holes are similar, only more dramatic. Now, let us return to singularity theorems, because they are often misunderstood. The theorems developed by Penrose, Hawking, and others do not simply say, there is definitely a tiny dot at the centre. They show that under certain assumptions, space-time becomes geodesically incomplete. Roughly speaking, some paths cannot be extended indefinitely in the classical framework. This indicates breakdown. But breakdown in the classical framework is exactly what one expects if quantum gravity becomes necessary. So the theorems are powerful, but they do not force literal infinities as final reality. They force the need for deeper explanation. That is subtler and more interesting. There is another clue that singularities may be placeholders. Physics generally dislikes infinities that arise from idealization. Point charges in classical electromagnetism create infinite self-energy unless treated carefully. Perfect continua create singular behaviours in fluid equations under some conditions. Sharp boundaries and zero-size assumptions often signal approximations rather than final ontology. Nature tends to regularize extremes. That does not prove singularities are unreal, but it makes skepticism reasonable. Now let us talk about density itself. Density is mass divided by volume. If volume becomes zero, density diverges. But what does volume mean inside a black hole where space-time geometry is highly curved and ordinary? Spatial slicing becomes coordinate dependent. Even defining volume cleanly can be subtle. This means the phrase infinite density may be less straightforward than it sounds. Popular explanations often compress several technical issues into one dramatic slogan. Useful for headlines, less useful for precision. There is also a philosophical angle worth enjoying. Singularities are places where language inherited from daily life becomes strained. Point, inside, centre, volume, time. All these words carry everyday intuitions formed in rooms, roads, and gardens. Black hole interiors may not respect those intuitions. We may need new concepts rather than stronger adjectives. That has happened before. Before relativity, time seemed universal. Before quantum theory, particles seemed tiny billiard balls. Before geology matured, continents seemed fixed. Reality repeatedly asks us to retire comfortable categories. Now, do we have any observational way to test interior ideas? Directly, not yet. The event horizon hides internal structure from outside classical observation. However, indirect clues may come from gravitational waves, black hole ring-down signals after mergers, Hawking radiation theory, information paradox resolutions, or subtle departures from classical predictions. Future observations may narrow possibilities. So while we cannot peek inside with a flashlight, and even if we could, several other issues arise, we may still infer the truth through careful external evidence. This is common in science. We infer atoms from scattering. We infer exoplanets from starlight wobble. We infer black hole interiors from mathematics plus indirect data. Now let us connect this to our central question. What is the densest thing in the universe? If singularities are literal, black holes win immediately. If singularities are not literal, then black holes remain the most compact known objects, but the exact densest internal state is unresolved. Perhaps a finite Planck-scale core, perhaps quantum geometry, perhaps something stranger. Meanwhile, neutron stars remain the densest confirmed matter we can model more concretely. So the answer depends on whether you value confirmed physics, classical extrapolation, or future theory. That is not evasive, that is accuracy. There is something comforting in this uncertainty. Even after centuries of progress, there are still places where our best equations say, "Continue here with caution." The universe still contains unopened rooms. Tonight we have stood at one of those doors, singularity or placeholder, final point or unfinished theory. Black holes have a reputation problem. Mention one, and most people imagine an object of absurd density, crushing everything into a tiny region, swallowing stars with grim efficiency, and generally behaving like gravity in an especially dramatic mood. This image is not entirely wrong. Black holes are among the most compact objects known, and their formation often involves catastrophic collapse. But the phrase, "black holes are infinitely dense," or even "black holes are the densest things," hides a subtle twist. Some black holes, especially the largest ones, can have surprisingly low average density. In some cases, lower than water. Lower than air? Usually not. Lower than water? Yes, for sufficiently supermassive black holes. This sounds like a trick, so let us proceed carefully. First, we need to distinguish between two ideas: local extreme gravity near the centre or horizon, average density calculated by dividing mass by the volume inside the event horizon. These are not the same thing. When people picture density, they often imagine material packed tightly throughout an object like lead, rock, or neutron star matter. But black holes are stranger, because their defining size grows with mass in a special way. For a non-rotating black hole, the event horizon radius is r sub s equals 2gm over c squared. This means radius is proportional to mass. Double the mass, double the radius, that seems ordinary enough, but volume scales with the cube of radius, so if radius doubles, volume increases by 8. If mass doubles while volume grows 8-fold, average density decreases. That is the key surprise. For black holes, as mass increases, the horizon grows linearly, but the enclosed volume grows faster. Therefore, average density scales roughly inversely with the square of mass. Bigger black holes can be less dense on average. Now let us make this intuitive. A stellar mass black hole formed from a collapsed star might contain several times the mass of the Sun within a horizon only tens of kilometers across. Its average density would be extremely high. A supermassive black hole containing millions or billions of solar masses has a horizon spanning millions or billions of kilometers. Enormous mass, yes, but also enormous horizon volume. Spread that mass over the notional volume inside the horizon, and the average density can become surprisingly modest. For the largest known supermassive black holes, the average can drop below the density of water. This does not mean they are fluffy. It does not mean you could swim in one. It does not mean the interior is a giant dark ocean. It means the ratio of mass to horizon-sized volume can be numerically low. Those distinctions are doing a lot of work. Now, why does this happen only for black holes and not for ordinary objects? Because ordinary objects are held together by material forces. A planet, star, or rock has structure determined by pressure, temperature, chemistry, and matter states. Black holes are defined geometrically by the event horizon. The horizon radius depends only on mass, and spin/charge complications in realistic cases, not on how tightly atoms are stacked in a familiar material sense. A black hole is not a giant ball of dense iron whose surface expands with more material. It is a space-time region whose no-escape boundary scales with mass. That makes average density a useful but potentially misleading statistic. Now let's compare examples. Earth has average density about 5.5 grams per cubic centimetre. Water is about 1 gram per cubic centimetre. The Sun averages around 1.4 grams per cubic centimetre. Surprisingly close to water because although its core is dense, much of its outer volume is diffuse gas. A neutron star averages around nuclear densities, astonishingly high. A stellar black hole averages high density too, but a supermassive black hole at a galactic centre can average much lower. The giant black hole Sagittarius A star, with around millions of solar masses, already has an average density far below neutron star levels. Even larger black holes can go lower still. This is one of those moments where math politely humiliates intuition. Now, let us be very careful about inside the horizon. When we calculate average density, we often take mass and divide by the volume of a sphere whose radius equals the Schwarzschild radius. This is a convenient classical estimate, but inside a black hole, ordinary notions of space are subtle. Spatial geometry is curved, coordinate choices matter, and the true interior structure is not a simple ball of homogeneous matter. So average density is not telling us the black hole is uniformly filled with low-density substance. It is telling us that if you use the horizon size as a notional boundary and perform the arithmetic, the result can be low. That is a bookkeeping fact, not an interior architectural blueprint. Think of it like population density for a country that includes deserts, mountains, and cities. One number can be true while hiding enormous complexity. Now, does low average density make large black holes less dangerous? Not remotely. Danger near a black hole depends on proximity, mass, spin, accretion environment, and tidal gradients, not the average density number. You could have a low average density supermassive black hole with an event horizon larger than planetary orbits, still capable of trapping light and dictating the motion of nearby stars. A taiga with low population density remains a taiga. Likewise, a black hole with low average density remains a black hole. There is another twist. For very large black holes, tidal forces at the horizon can actually be gentler than for small stellar black holes. Because the horizon is larger, gravity gradients there can be smaller. So crossing the horizon of a supermassive black hole, in principle, might be less immediately destructive than crossing near a small one. The later consequences remain poor, but again, size changes intuition. This is why black holes are such good teachers. They force us to separate concepts we casually merge. Mass is not size is not density, average density is not local intensity, compactness is not danger in a simple linear way. One word can hide many variables. Now let us connect this back to our broader story. We began with ordinary density. Wood floats, stone sinks. Then atoms revealed hidden empty space. White dwarfs compressed matter beyond ordinary solids. Neutron stars pushed beyond atoms. Quark matter and strange matter invited deeper speculation. Black holes seemed like the obvious final champions of density. And then they complicated the contest. A stellar black hole can be fantastically dense on average. A supermassive black hole can be less dense than water on average. Yet both possess event horizons. Both trap light once crossed. Both can dominate surrounding space. So asking, what is densest, requires precision. If we mean densest confirmed material matter, neutron stars are leading contenders. If we mean classical endpoints of collapse, black holes dominate compactness. If we mean average density by horizon volume, some giant black holes are surprisingly modest. This is why science loves definitions. Now there is also something philosophically satisfying here. The largest black holes often live in galactic centres, enormous and influential. They shape star orbits, power quasars when feeding, and participate in galaxy evolution. Yet by one metric, they are not hyper-dense monsters, but vast regions whose average density can be unexpectedly low. Power does not always look like compression. Influence does not always require hardness. Scale changes meaning. The universe repeats this lesson often. A giant red supergiant star can be huge but diffuse. A neutron star can be tiny but crushingly dense. A supermassive black hole can be enormous but low in average density. Appearances negotiate constantly with physics. Now imagine explaining this to someone centuries ago. There exist invisible objects heavier than millions of suns, larger than planetary orbits, from which light cannot escape, and some are less dense than water on average. You would not be invited to finish dessert. Yet today, it is a respectable statement in astrophysics. That progress is worth appreciating. Now, where does this leave our original question? What is the densest thing in the universe? Some questions sound simple because they are short. What is the tallest mountain? What is the fastest animal? What is the hottest place? What is the densest thing in the universe? Short questions often arrive wearing the disguise of clarity. They seem to request a neat answer, preferably one word long, perhaps with dramatic music behind it. But some questions are not really asking for a winner. They're asking us to inspect the categories we use. Tonight we have reached that moment. What is the densest thing in the universe? After everything we have explored, the most honest answer may be this. It depends what you mean by dense. That is not evasion. That is progress. Let us begin with ordinary density. In daily life, density means mass packed into volume. A rock sinks in water because it is denser. Wood floats because it is less dense. Oil separates from water. A suitcase becomes suspiciously difficult to lift because someone has packed too much into too little space. This definition works beautifully for everyday materials. Then we meet stars. A giant star can be enormous but relatively diffuse in outer layers. A white dwarf can be Earth-sized yet contains solar mass. A neutron star can be city-sized with more mass than the Sun. Already density stops being intuitive. Then black holes arrive and make things worse in a productive way. If we calculate average density using event horizon volume, some supermassive black holes can have surprisingly low values compared with water, yet they still trap light. So average density is no longer enough to capture what matters physically. The contest has broken its own scoreboard. Now let us separate the meanings hiding inside the question. If by densest thing you mean densest confirmed stable matter we understand reasonably well, then neutron stars are leading candidates. Their interiors compress matter beyond atoms. Their densities approach or exceed nuclear scales. They are observed, measured, timed, merged, and studied across multiple methods. This is a strong answer. If by densest thing you mean densest possible state of matter, then speculative contenders appear. Quark matter, strange matter, exotic phases in compact star cores. These are scientifically serious possibilities, but not settled winners. If by densest thing you mean most extreme gravitational compactness, black holes dominate. Enough mass confined within a near event horizon changes causal structure itself. Light cannot escape once crossed. That is not ordinary density, but it is a kind of ultimate compactness. If by densest thing you mean literal infinite density, then singularities from classical relativity would win instantly. But whether singularities physically exist or signal incomplete theory remains unresolved. So even the dramatic answer comes with an asterisk large enough to deserve its own constellation. This is why the question evolves from which object wins into which definition are we using. Science often advances exactly this way. At first we ask, what is time? Later we ask, do you mean measured duration, thermodynamic arrow, psychological experience, relativistic proper time, or cosmic expansion history? At first we ask, what is light? Later we ask, do you mean wave behavior, particle detection events, electromagnetic field excitations, or human perception? At first we ask, what is the densest thing? Later we ask, do you mean matter, geometry, average mass concentration, quantum limits, or observationally confirmed states? The deeper question becomes the real discovery. Now let us appreciate what density has taught us. We began with floating and sinking. Then atoms revealed that ordinary matter contains surprising empty space. White dwarfs showed electrons resisting collapse. Neutron stars showed matter beyond atoms. Pulsars turned dense remnants into clocks. Magnetars added impossible-seeming magnetic strength. Quark stars and strange matter reminded us that interiors may still surprise us. Black holes shifted the story from matter under pressure to space-time under siege. Singularities forced us to ask whether infinities are reality or warning signs. That is an extraordinary amount of learning hidden inside one short question. Sometimes the best questions are not the ones with easy answers. They are the ones that open doors. Now let us consider another meaning of density, information density. A single teaspoon of neutron star matter contains astonishing mass in tiny volume. Likewise, a short sentence can contain astonishing insight in few words. What is the densest thing in the universe? Turns out to be dense in this second sense. It packs cosmology, particle physics, relativity, quantum theory, observational astronomy, philosophy of science, and the limits of language into 7 words. The question itself is compact. Perhaps that is why it is so satisfying. There is also emotional value in rethinking the question. Many people want science to be a cabinet of labels. Tallest mountain? Done. Nearest star? Done. Densest thing? Done. But reality is often more relational. Things depend on context, scale, method, assumptions, and what exactly is being measured. That does not weaken truth, it refines it. Precision is not complication for its own sake. Precision is respect for reality. Now let us ask something gentler. Why are we drawn to extremes at all? Biggest, smallest, fastest, hottest, densest. Partly because extremes help the mind map boundaries. We learn what is possible by visiting the edges. A neutron star tells us what matter can endure. A black hole tells us what gravity can do. A singularity tells us where theory may fail. Extremes are educational landmarks. They are the cliffs around the landscape of knowledge. But cliffs are not the whole terrain. Most of the universe is not neutron stars or black holes. Most of your life will not involve quark matter, hopefully. Yet by understanding extremes, we better understand the ordinary too. Atomic structure explains materials. Gravity explains planets. Pressure explains weather. Quantum rules explain chemistry. The far edge teaches the nearby centre. This is one reason astrophysics feels so satisfying. Remote objects illuminate familiar life. Now let us revisit black holes briefly. People often ask whether black holes are things in the same sense stars are things. That itself is revealing. A star is matter with layers, fusion, atmosphere. A black hole is partly matter's outcome, partly geometry's regime, partly thermodynamic puzzle, partly information paradox. Calling it a thing is correct but incomplete. Likewise, asking if it is densest is correct but incomplete. Language built for stones and apples works hard in deep space. Now, if a listener tonight insisted on one concise answer, we can offer tiers. Most defensible observe dense matter, neutron stars. Most compact objects with horizons, black holes. Most extreme classical extrapolation, singularities. Most intriguing hypothetical denser matter state, strange quark matter or related phases. Most educational answer, the question needs refining. That final one may be the best. There is something peaceful in realizing not every question ends with a trophy ceremony. Sometimes the answer is a map. Sometimes the answer is vocabulary improved. Sometimes the answer is learning what you really meant to ask. And perhaps the densest thing we encountered was not a star or hole at all, but the concentration of mystery inside seemingly simple words. At first glance, this sounds like a forbidden question. Could anything be denser than a black hole? Surely not. Black holes are the final bosses of compression. They trap light, bend space-time dramatically, and have reputations so intense that even people who have never studied physics speak of them with automatic seriousness. If anything wins the density contest, surely it is the black hole. And yet, as we have learned, black holes make simple comparisons difficult. Some supermassive black holes can have average densities lower than water when calculated over the volume inside their event horizons. Singularities may or may not be literal physical infinities. The event horizon is a boundary, not a material surface. Interior geometry is not fully settled in quantum gravity. So asking whether something could be denser than a black hole turns out to be less like asking who is taller and more like asking whether silence is louder than music. We need definitions first. Let us begin with one useful meaning. If by denser we mean more mass packed into less volume as ordinary matter, then neutron stars already compete strongly against many black holes on average density calculations, especially compared with gigantic supermassive black holes. A neutron star is made of matter in a recognizable, if extreme, physical state. It has a surface, layers, pressure support, and material structure. A black hole is not simply a ball of denser matter. It is a region enclosed by an event horizon where escape is impossible. That distinction matters. So yes, in one sense, some neutron stars can be denser than some black holes if you compare average density numbers. This sounds scandalous until one remembers we are comparing different categories. Now let us ask a deeper version. Could there exist stable matter states denser than neutron star matter and denser than any meaningful pre-horizon compact matter? Possibly. That is where quark stars and strange stars enter. If quark matter or strange quark matter form stable compact objects, such stars might be more compact than ordinary neutron stars of similar mass. They could represent denser stable matter than anything we have confirmed directly so far. Still, if enough mass is confined into too small a region, collapse to a black hole may occur. So nature may allow denser matter up to a limit, then replace the matter story with the horizon story. Now let us consider the phrase denser than a black hole in classical relativity. If one takes the singularity literally, then the center of a black hole has infinite density. Nothing beats infinity in ordinary arithmetic. Contest over, trophies cancelled. But many physicists suspect singularities indicate incomplete theory rather than actual physical infinities. If quantum gravity resolves the center into a finite ultra-dense state, then infinite density disappears as a literal answer. That reopens the question. Perhaps the true core density is finite but beyond neutron star scales. Perhaps some hypothetical pre-black hole matter phase could approach it. Perhaps density itself ceases to be the right language there. This is one of the most important possibilities. Maybe the question fails before reality does. When space-time becomes strongly curved and quantum effects dominate, volume and localization may not behave as classical intuition expects. Density equals mass over volume sounds simple, but what counts as volume deep inside a black hole may be subtle. So something denser than a black hole may be grammatically neat and physically confused. The universe sometimes answers by rejecting the premise. Now let us explore speculative possibilities people imagine. Planck density objects. At the Planck scale, where quantum gravity becomes central, one can define characteristic densities enormously beyond anything in neutron stars. Some theoretical models propose black hole interiors reaching or capped near such scales. These would be vastly denser than known matter, but no confirmed object lets us casually point and say, there it is, the Planck nugget. Primordial exotic remnants. Some theories suggest tiny black hole remnants, or ultra-compact stable leftovers from early universe processes. Again, intriguing. Again, unconfirmed. Boson stars. Hypothetical compact objects made of bosonic fields rather than fermionic matter have been proposed. Depending on parameters, some could be very compact, though whether they surpass black hole-like compactness while remaining horizonless depends on the model. Reality has not yet RSVP'd, so the honest frontier answer is perhaps, but evidence is pending. Now let us turn the question around. Could anything be more compact than a black hole without being a black hole? That is even trickier. For a given mass, if an object is compressed within its Schwarzschild radius, ignoring rotation/charge complications, an event horizon forms. So becoming more compact than the relevant black hole threshold generally means becoming a black hole. That is why black holes are special. They are not just dense objects. They are the compactness limit where geometry changes category. This means there may be denser matter than neutron stars, but once enough mass is squeezed too far, the horizon appears and the comparison changes language. Now let us use an analogy. Imagine stacking books on a shelf. Up to some point, shelves hold. Past that, shelves bend. Past another point, the whole furniture category stops being the right model because the wall fails. White dwarfs are one shelf. Neutron stars are another reinforced shelf. Quark stars may be an upgraded speculative shelf. Black holes are what happens when shelving has ceased to be the relevant engineering discipline. At that stage, architecture has become geology. Not a perfect analogy, but it helps. There is also a philosophical lesson here. Humans like ranking questions because they feel decisive. Biggest whale, fastest sprinter, highest mountain. But physics often responds with category questions. Do you mean mass, speed and vacuum, average height above sea level, prominence or surface gravity? Likewise, could anything be denser than a black hole? Do you mean average density, core density, stable matter density, compactness threshold, or literal singularity? Once clarified, the answer becomes richer. Now let us offer concise versions. If you mean average density, yes, some neutron stars exceed some supermassive black holes. If you mean stable matter density, maybe quark or strange matter could exceed neutron star matter. If you mean classical infinite singularity density, no, nothing exceeds infinity. If you mean physically confirmed interior density of black holes, unknown. If you mean compactness threshold for a given mass, black holes are effectively the limit. That is a lot of answers for one sentence, which usually means it is a good sentence. There is something satisfying in realizing black holes do not merely dominate because they are most extreme. They dominate because they force us to rethink what comparison means. Matter comparisons become geometry comparisons. Density comparisons become causal structure comparisons. Ranking becomes theory choice. That is a more interesting victory. Now step back beneath the night sky for a moment. Somewhere neutron stars spin like clocks. Somewhere magnetas crack and flare. Somewhere compact binaries spiral inward. Somewhere supermassive black holes anchor galaxies. And somewhere in equations still being written, there may be states of matter denser than anything yet confirmed. The universe has not promised us the final list. That uncertainty is part of the beauty. Tonight we have asked whether anything can be denser than the most famous dark objects in space, and the answer was not a simple no. It was a doorway, and through that doorway waits our final reflection. After all these crushed atoms and invisible horizons, what does the search for the densest thing actually teach us about reality itself? Now we arrive gently at the end of our journey. We began with a simple question. What's the densest thing in the universe? It sounded like the kind of question that might fit neatly into a sentence. Perhaps a tidy answer. Perhaps a dramatic name followed by satisfying certainty. Instead, it opened into stars, atoms, gravity, collapse, quantum resistance, invisible boundaries, and the places where mathematics itself becomes unsure. That is often how the universe responds to curiosity. You ask for one fact. It offers an entire landscape. Tonight we move from ordinary objects that float or sink, to the hidden emptiness inside atoms, to white dwarfs where electrons hold up dead stars, to neutron stars where matter collapses beyond chemistry itself. We listened to pulsars keeping time with remarkable patience. We met magnetaires whose fields are so intense that reality behaves differently nearby. We step cautiously toward black holes, where return becomes impossible once a certain boundary is crossed. We looked at singularities and found not certainty, but honest mystery. And along the way, the original question changed shape. The densest thing was no longer just an object to identify. It became a way to understand what matter does under pressure, what gravity does when unopposed, and what science does when answers become difficult. There is something comforting in that. Many people quietly assume knowledge works like shelves in a library, Every question has a book. Every book has a page. Every page has a sentence. Find the sentence and the matter is settled. Sometimes that happens. But many of the best questions are not shelves. They are doors. You open them expecting a room. You find a horizon. That is not failure. That is discovery. Now, let us return to density itself. In daily life, density means weight in a small space, heavy stone, solid metal, packed luggage that seemed reasonable at the time. It is practical, measurable, familiar. But in the cosmos, density becomes something more profound. It reveals how much emptiness ordinary matter contains. It reveals that stars can die and still endure. It reveals that particles obeying tiny quantum rules can hold up objects larger than worlds. It reveals that enough mass in one place can bend time, redirect light, and reshape the future paths of anything nearby. Density, in the end, is not just about heaviness, it is about consequence. A neutron star is small yet powerful. A black hole may be dark yet transformative. A compact question may contain years of thought. The universe likes concentration. There is also a human parallel here. Some of the heaviest things in life are not large. A memory can weigh more than furniture. A sentence can stay with you for decades. A silence can fill a room. A choice made in 1 minute can shape years. Importance is often dense. Meaning is often compact. Perhaps that is why we recognize something familiar in these cosmic extremes. They mirror truths we already live with in quieter forms. Now think of the stars overhead. Most points of light in the night sky appear calm, steady, distant, decorative almost. Yet hidden among them are collapsed remnants denser than imagination once allowed. Some spin hundreds of times each second. Some flare with magnetic violence. Some anchor galaxies invisibly. Some may contain phases of matter we have never touched or fully understood. The sky is not merely beautiful. It is busy with secrets, and still it hangs there in silence. That silence matters. The universe does not announce its complexity loudly. It lets us notice slowly. Through careful measurement, through patient theory, through generations of people asking questions no immediate survival task required. That may be one of the loveliest things about science. It is curiosity made durable. Someone looked at a point of light and wondered what it was. Someone else built equations. Someone else built telescopes. Someone else compared signals. Someone else doubted an old answer. Someone else refined a definition. And now, here you are, perhaps lying comfortably in the dark, listening to the result of countless minds reaching outward across time. Knowledge itself has density. It packs many lives into one understanding. Now, let us be honest about uncertainty. We do not know everything inside neutron stars. We do not know the final truth of singularities. We do not yet possess a complete quantum theory of gravity accepted by all. We may discover stranger matter, deeper principles, or entirely new categories in years to come. This incompleteness is not a flaw in science. It is the pulse of science. A finished universe would be less interesting. An unfinished one invites participation. There is room for future minds. Perhaps that future includes someone listening tonight. Now, if the question were asked one final time, what is the densest thing in the universe? We could answer in several ways. Neutron stars for confirmed matter, black holes for ultimate compactness, singularities if classical infinities are literal, unknown quantum states if tomorrow surprises us. But after all we have seen, another answer feels equally true. The densest thing in the universe may be mystery itself, so much contained in so little. One dark object in the sky, one unexplained signal, one unresolved equation, one simple question, and from it whole worlds of thought. As the night settles around you, perhaps take comfort in that weight, not a crushing weight, a steady one, the weight of existence being richer than it first appears, the weight of stars that died and still matter, the weight of questions that keep opening. the weight of knowing that even in a vast universe, meaning can gather densely in small places. Thank you for spending this quiet time here with me. Wherever you're listening from, I hope the night feels a little wider and a little gentler now. And as you drift towards sleep, the stars will continue their patient work above you, spinning, cooling, collapsing, glowing, waiting for the next question.